not every kind of solution would require deep learning. Just like not every situation will benefit from large language models usage. We know that if we develop a sense of which kind of techniques and methods work under which circumstances the best, we will be able to optimally use our resources. Otherwise, we may end up generating a lot of carbon footprint and do exactly against the thing what we are fighting against to make the world sustainable in ways that we can. Challenges are many. For example, if we talk about the initiatives like Gemini, or for that matter, OpenAI's work, or the resultant things including ChatGPT 4 and so on, we all realize that there are so many different kind of models in place for different purposes. They're not interchangeable all the time. But one thing that we have seen, although many of the things have been improving, including that of ChatGPT's performance in certain criteria, we know they depend on large amount of the data available of historical kind, and their ability to do certain things also gets limited to a certain extent by what kind of data they have seen earlier. Their being clean and correct also plays an important role. Even in video image video or image interpretation and identification of context, or identifying elements from the video or still image and then explaining it or expressing it into either textual form and identification of context, generating the or identifying voice in synthetic way using one of the synthetic speech generators for those who are visually impaired. For some of those things could be some of the things which many people may have seen across in literature being attempted. So which direction you as researchers will take or are interested in depends on what you find of interest over there. My suggestion as a fellow academic shall be that whatever is taught and shared, please consider in trying to see whether it answers the questions that you had at the back of your mind when you start this FDP. If it does, of course, that helps. But if it doesn't, please feel free to ask any queries you have at the back of your mind. Sometimes in literature, there could be arguments and counter arguments. Both might have their own benefit. Please feel free to see if there are ways that beyond the FDP sessions, there could be a way to connect to the resource people at their convenience using whatever method works mutually for you. And I wish each one of you all the best and a wonderful experience ahead. Thank you so much.
Thank you, Professor Banerjee. We really appreciate you joining us here and sharing your words of encouragement and motivation to the participants. I'll request Dr. Rajbir Kaur, Head of the Computer Science and Engineering Department, to also share her wisdom with us.
Good evening, everyone, and welcome to this program. So this program is organized by the Department of CSE in collaboration with the Intermedia Research Group. So I would like to brief you about the institute, the LNMIIT, and the Department of CSE, the programs that are running. So I use this platform to tell about that. So LNMIIT Jaipur is a prominent university located in Jaipur, Rajasthan. And it is established in 2002 by Lakshmi Narayan Mittal, who's a renowned steel magnate. And the institute aims to provide quality education in the field of information technology, engineering, and related disciplines. The LNMIIT programs are recognized by UGC and AICTE. And the Department of CSE offers a BTech program in CSE with specialization in AI and DS. And the focus is on fields that you will be studying in this workshop like computer vision and deep learning and applications of these. The department also offers MTech program in computer science with specialization in AI and DS. The department is equipped with state-of-the-art infrastructure, and it has modern laboratories and servers to do research on AI, DS, and deep learning. So there is a strong emphasis on R&D in the department, and it even our students, our BTech students and MTech students, they are participating. They are publishing lots of research papers and also participating in hackathons where they have won awards. So and the department also has centers which is focusing on technology and innovation. The LNMIIT also has strong industry collaborations and robust placement cell that ensures that students receive opportunities to work with top companies. The faculty is highly qualified and has PhD degrees from IITs and NITs. And we have also professors who are collaborating with us from abroad. So that's all about the Department of CSE and the Institute. And this program requires from the people who are attending. I congratulate you all and welcome you all to this program. Congratulations also to the organizers, Dr. Preeti and Dr. Nikansh Biharikar, for organizing this event. Thank you.
Thank you, Dr. Rajbir. So right now the floor is open for any questions or any concerns that you might be having regarding this FDP. Since our session, the first speaker would be joining us at around 6:30, Professor Sumantra Datta Roy from IIT Delhi. So in case there are any questions, please let us know in the chat box, and we'll try to address them as to the best of our capabilities. So if there are any questions, please let us know. Please type in your message in the chat box. All right. It seems like
Please type
like
in
we are
your
all clear
message
with
in the
all the
chat
rules
box.
and regulate the policies of how the attendance. Okay. Smita Jha, she wants to know how the assessment will be done. So the assessment will take place on the last day of the FDP, which is on the 14th of December. It will be in online mode again. It seems
And
like
it will be
type
through
in
the
your
message
ATAL
in the chat.
portal. So since all of you have signed in at the ATAL portal, so the assessment would be uploaded on the portal, and through that portal only you will be and it will be a multiple choice assessment. So I think we will be you will have to access the ATAL portal for the assessment. And also, Hemant wants to know, please provide the material of the FDP. I would also like to inform you that all the sessions are being live streamed on YouTube. So if you go on YouTube and if you check ATAL FDP on deep learning for vision and language, you will be able to see all the sessions over there. However, despite that, I will be uploading the videos in a shared Google Drive, and I will be sharing the link of that drive with you, so you can go through these the recorded sessions as well. Okay, so Nitin wants to know if there is any session on digital footprint. As of now, I don't think there is any particular session on digital footprint, but yes, we can explore with our experts whether they would be willing to talk about it or not. But yeah, I would encourage you, Dr. Nitin, that during your engagement with the experts, if you can discuss this part also with them. Dr. Hemant, if I get the slides from the experts, I will definitely provide them to you. The slides and the PPTs, I will provide them if the experts share them with me. So, any other question?
Okay, ma'am.
Yes, yes, thank you. So, is there any other question that anyone would like to ask? Maybe you can unmute yourself also and you can interact in case you want to ask something. Okay, in that case, what we will do is we will wait for 10 minutes and we will wait for our expert to join in at 6:30 and we will begin our first session, which is Introduction to Transformers. Yes, Dr. Harkiran, the session recordings will be shared with the participants, though you will just though kindly allow us 1 day lag time for us to upload these recordings. So today's recordings will be uploaded by
Ma'am, one
tomorrow.
thing. Can I ask one thing?
Yes, yes, sure, Dr. Hemant. Yes, yes, please.
Yeah, ma'am. If you can provide the slides before the starting of the session, we can go through the slides.
Dr. Hemant, if the experts share the slides with me before the sessions, I will provide them to you. Else, whenever they do, I will upload them on the shared folder. So I do not have access to all the expert slides right now. Okay?
Okay. Thank you,
Okay,
ma'am.
all right.
Preeti ma'am, I have one doubt.
Yes, Dr. Reena?
Uh, I'm not yet doctor, sorry for that.
Yes.
Yeah.
I hope you will become one soon.
Yes, very soon.
Yeah,
Thank you.
okay.
Ma'am, I wanted to ask you that will the MCQ test will be under the supervision because my laptop's camera is not working.
All
So will
right.
it be necessary?
So actually, we have not received any like guidelines about the assessment from AICT as of now, but we will get in touch with them and ask them how they are going to manage the assessment and how we are supposed to take care of this. So
Okay.
we maybe if they say that your cameras have to be turned on during the assessment, then I would advise you to take the assessment from a system whose camera is working.
Okay, ma'am.
All right. Okay. So anything else? Okay. So we will wait till 6:30 and start our new session at 6:30. Thank you all for joining once again.
प्रीति मैडम नमस्ते। मेरी आवाज आ रही है क्या? प्रीति मैडम नमस्ते। मेरी आवाज आ रही है क्या?
Professor Dattala, we are able to hear you. Thank you for joining us.
ओ नमस्कार सर। प्रीति मैडम नमस्ते।
That's-
व्हाट अ प्लेजेंट आवाज आ रही है क्या?
Professor, same here, sir.
सर आप खुद शरीक हैं, ये तो हम तरुण लोगों के लिए नमस्कार सर। प्रीति मैडम
बस कुछ कुछ आपसे सीख रहे हैं.
अरे सर और आप खासकर राहुल बैनर्जी सर, आप शर्मिंदा मत कीजिए। और कोई कहे तो दूसरी बात होती है, लेकिन आप मत कहिए।
So kind of you, sir.
थैंक यू सर।
So Professor Roy, do I have your permission to record this session?
बिल्कुल बिल्कुल बिल्कुल।
Okay.
तो जो गलतियां हैं सारे बिल्कुल सारे भरी सभा में तो सबको याद ही होंगी, इंटरनेट पे भी आ जाए। जरूर मैडम, जरूर।
So we have the pleasure of having Professor Sumantra Datta Roy today for the first session on this ATAL FDP on deep learning for vision and language. The title of his talk is Introduction to Transformers. And here is a brief introduction to Professor Roy. I would also like to inform everyone that I have had the honor of studying with his legendary father, Professor S.C. Datta Roy from IIT Delhi. So Professor Sumantra Datta Roy is a BE Computer Engineering from DIT Delhi, 1993. He completed his BE and then he's completed his MTech and PhD degrees at the Department of Computer Science and Engineering from IIT Delhi in 1995
Professor
and
Sumantra Datta
2001
Roy is a
respectively.
BE Computer
He
Engineering
started his
from
career
DIT
in teaching
Delhi,
and research in the
1993. He
Department of
completed his
Electrical
BE
Engineering at
and then he's
IIT
completed his
Bombay,
MTech
where he
and
worked
PhD
from
degrees at the
2001
Department of
to
Computer
early
Science and Engineering
2007
from IIT
as an
Delhi.
assistant
In
professor.
1995,
From
Professor
2007 to
Sumantra Datta
2001
Roy is a
respectively,
BE
he
Computer
was he
Engineering
started his
from
career
DIT
in
Delhi,
teaching and
since
research
2018
in
he
the
has been a
Department of
professor in
Electrical
Electrical
Engineering at
Engineering
then he's
IIT
completed
Bombay
his
at
MTech
IIT
where he
Delhi.
worked
PhD
from
degrees at the
He was a
Department
visiting
of Computer
faculty
Science
member
and
as an
Engineering from
external
IIT
as an
Delhi
assistant
in
professor.
2005
From
and
2007 to
2001
2001 he's a
respectively.
recipient
He
of
was
the
in
he started his
2004
career
IIT
in
and
teaching and
since
research
2018
in
he
the
has been a
Department of
professor in
Electrical
Electrical
Engineering and
Engineering
then he's
IIT
completed
Bombay
his
at
MTech
IIT
where he worked
Delhi
from
in
2001 he was a
2001 the
visiting
Department
faculty
of
member
Computer
as
Science
an
and
external
Engineering
as an
IIT Delhi
assistant
in
professor.
2018.
He has been an
And
from
Professor
2007 to
Sumantra Datta
2001
Roy
he's
is
a
a BE
recipient of
Computer
he started
Engineering
his
from
career
IIT
in
Delhi
teaching and
since
research in the
2019 he has
Department
been
of
a professor
Electrical
in
Engineering
Electrical
and then
Engineering
he's
IIT
completed his
Bombay at
MTech where he
IIT
worked
Delhi
from
in
pattern recognition and machine learning, medical informatics, biometrics, video and image coding, music information retrieval, and bioinformatics. So, Professor Datta Roy, over to you for your presentation.
Madam, thank you very much. And I think I must inform everybody, including the August audience, wherein the director, Professor Rahul Banerjee himself, is here gracing the occasion. And I've also admired Preeti Madam because her covariance matrix has an extremely high norm. She's an electrical engineering by training. She has her master's in VLSI design and then now is a computer scientist. So there are very few areas which she hasn't touched. She's also the daughter of a famous teacher, and I consider myself lucky to be her junior at IIT Delhi.
Thank you
Madam,
so much,
thank you
Professor.
very much. Thank you very much for the kind words. And just before I start, let me try to share my screen. Also, I'll just have a little bit of a disclaimer that I actually don't know this area too well. So the way that I started, and in fact, as it said, the best way to learn is to try to teach. So that is what I'll be trying today. And also because okay, I'll come to it as we get to the slides. So I'll possibly and Preeti madam, would it be possible to have this in an interactive mode? Would you allow participants to unmute their microphones and
Yeah,
speak?
of course. Yes, they
Oh,
have the
that will be
privilege to
wonderful.
unmute yourself, and
That will
we
be
have
that will be
like
wonderful.
yes, yes. Yeah, so I'm
And
again requesting all participants to please engage with Professor Roy, and he will be like your mentor for this session and in future as well. So you can like explore how you can use his the knowledge that he's going to share today in your future research.
madam, these are great expectations. Rather than a mentor, I might end up being a tormentor. Okay.
Okay.
Okay, let me start with my slides. I hope this will be visible right now. And you can see my cluttered desktop. It actually is a reflection of my cluttered table also. Even my physical desktop is extremely cluttered. Well, I call it the entropy is very high. Entropy not in an information theoretic sense, but in the actual physics sense of it as the measure of disorder. Okay. So this is on like today almost all of us, even little kids, talk about chat GPT, talk about large language models, and I'll be trying to get get to some of the technologies behind transformers. And my covariance matrix is not as high norm as Preeti Madam's, but I have essentially tried to look at it both from the point of view of a computer scientist as well as from the point of view of an electrical engineer, and where some of these two lovely disciplines seem to merge, and where are they different, and how this would go ahead. So, in fact, I'm thankful to Preeti Madam because I'd like to start with this little video, which was a little advertisement for Pepsi, wherein I'm unfortunately an over the hill researcher, and I'm trying to be at least a good teacher, but then I don't know, my situation is pretty similar to what is shown here. I'll start with this video. Most of you might have seen this particular advertisement for Pepsi. So this is our Indian heartthrob Shah Rukh Khan. He wants to have a Pepsi, and this was during the World Cup. So he dresses up as Sachin and then goes into the dressing room where he cites some Pepsi. So this is like Sumantra. This is like Sumantra trying to achieve some greatness through research. It's absolutely impossible. Look, I'm hiding just like Shah Rukh Khan is. And he goes to Rahul Dravid and says, "Ha, Saurav, pile pile." So he's making such mistakes when the organizer tells him, "Well, it's now your turn for the lecture." And just like Shah Rukh Khan here, and the actual Sachin comes and says, "Well, Sachin doesn't take the bat from him, but rather takes the Pepsi." And this is my situation. Aha. Okay. So I hope you'll forgive me for my mistakes here. I'll I'll start off with this particular paper, which sort of changed almost everybody's perspective into whatever they were doing. Because the title of the paper, the 2017 paper, is Attention is All You Need. And unfortunately, for people like me who are not really from the area, it turned out to be not attention, but tension is all you need. So, well, I was literally forced to try to learn at least something about this particular paper. Some of these concepts I was rather forced to know, and I'll just try to present a little bit. So, I actually do not know all the nitty gritties of transformers, but I'll try to present I'll try to abstract out the nitty gritty details and try to present some of the basic concepts behind that. For instance, I will not be able to tell you too many details about, let's say, the 512 length vector, which was used in the basic transformers paper, or the the sort of vectors which are used, or the sort of matrices, because everything is presented in the form of matrices: the Q matrix, the K matrix, and the V matrix, which essentially stand for the queries, the keys, and the values. On the other hand, I'll tell you how the similarity is actually computed. So this will stress more on some of the very basic things along with a little bit of a historical perspective. So this was the paper on transformers. And in fact, one of the questions that first comes to one's mind is, why are these sort of architectures called transformers? Is it this? Well, it's a completely different kind of beast altogether. So, if Optimus Prime and Bumblebee are the sort of transformers that appeal to you, well, that's actually good. Okay, this is a different kind of beast altogether. Then this, the electrical transformer with its two windings, wherein the voltage ratio is in the ratio of the number of turns and the current is in the opposite ratio. That is an electrical transformer. Here, this particular architecture is called a transformer because it was traditionally, the basic idea came from natural language processing, that is given a particular sequence. The idea was to have a sequence translation. Okay, so to translate a sentence or a set of sentences in one language to another language. So in that sense, it was essentially a transformation. So that is why this particular architecture is called a transformer architecture. Well, some of these ideas are actually not very new. If one looks at a little bit of history or forget history, if one just looks at one's own mobile phone, let's say typing a message in WhatsApp, there is often a choice of three words as the next word, which at least the app should pick up. So there is a suggestion of three words. So that is also next word prediction. Then how is a transformer really different? Well, what is there in our mobile phones? This next word prediction is typically either a 2 gram or a 3 gram, which is typically the idea behind an n-gram is to predict on the basis of the last couple of words to predict the next word. Now, the one of the things which all of us would have experienced with, let's say, this next word prediction on one's mobile phone is that often sentences, there is no guarantee that they will be grammatically correct. There's a very good chance that the entire sentence is grammatically incorrect. On the other hand, with the sort of chat GPT like interfaces, what we see today is not just does this architecture seem to understand the syntax of the English language. In many cases, there is some understanding of the semantics as well. So if we look at a little bit of the history behind this, actually there is a structure or an order in randomness, and that was discovered way back in 1913 by the famous physicist and mathematician Markov, who observed that letters or words, let's say in the English language, do not appear at random. For instance, so here, this is Markov. Markov made an observation that, for instance, if one has a letter Q, the next letter which follows Q would almost invariably be a U. Okay, and some of the other things which Markov had observed at this particular point in time was that the frequency of some alphabets is actually quite high. For instance, the most common alphabet in the English language is E. All right. In fact, this is also something which electrical engineers study in communication, wherein this is essentially the idea behind some coding strategies such as the Huffman code. And in fact, in order to know what the Huffman code is, sometimes it's actually better to read up Sherlock Holmes. So the frequency concept was actually there. If you read up, see, there are four essential texts of Sherlock Holmes. The compilation of stories, which is the adventures of Sherlock Holmes, has a story called The Adventure of the Dancing Man. So if you actually go back and read The Adventure of the Dancing Man, believe me, you will understand. If you don't know what Huffman coding is, you'll understand it perfectly. It is based on, see, there is a particular code wherein Sherlock Holmes is able to decode that, and he assumes a one-to-one correspondence behind a set of dancing figures which are written by a criminal, and he writes a sentence in the same code, and the criminal comes in understanding it, and he's able to catch him. So the very fact that, let's say, the symbol which occurs most often in a very large piece of text, that is the alphabet E. And the fact what Markov observed was that the probability of a letter happening in a word actually depends on the letters before it. For instance, if there is a Q, then the next letter almost invariably has to be a U. So there is a strong probability. The next alphabet is not completely at random. And this concept also extends to words. So after a word, the next word is not completely at random. So the first formal study of predicting the next letter or next word was done by Markov. And it is also not unusual to imagine the grand man of information theory, Claude Shannon, also doing a study on it. So Claude Shannon essentially looked at entropy. So I talked about the entropy in on my physical desktop as well as the computer desktop. But Shannon looked at entropy in an information theoretic sense. And what he looked at was he had a treatise on the prediction of entropy for English letters. Okay, so he extended the probabilistic analysis to getting the information content in a letter, in a word, how he would compose that out of probabilities. So, this is the work of Shannon in this regard. Well, by the way, Shannon also has some other very important contributions which sometimes we forget. And in fact, it is also interesting that it was Shannon who observed in 1938 the correspondence behind what traditionally was taught in philosophy as logic. So that's propositional logic and as well as predicate logic. He observed a correspondence between that, then an abstract algebra, which was created by mathematician George Boole in 1853 or 1854, and switching circuits, which, if you remember the year which I just mentioned, 1938, 1938 was when Howard Aiken at Harvard University created the first electromechanical computer. He called it Harvard Mark I. And in fact, today in electrical engineers in digital signal processing talk in terms of the Harvard architecture. So there is the von Neumann architecture wherein there is a single memory for data and instructions. There is the Harvard architecture wherein there are separate memories for data and separate memories for instructions. So this Harvard architecture came about then. And all that we have to thank this gentleman, this grand old man of information theory, who actually observed that all three of these, whatever people were studying in philosophy, whatever the abstract algebra of George Boole was, and switching circuits all corresponded to one and the same thing. Fascinating. And closer to home, we would remember Mahalanobis. Professor Mahalanobis was the founding director of the first institute for statistics anywhere in the world, the ISI, the good one. I mean, not the one which is associated with our friendly Western neighbor, our country, which is the country which is our friendly Western neighbor. No, not that, but Indian Statistical Institute. So Professor P.C. Mahalanobis, who's also associated with, like nowadays everybody knows in machine learning, there is something called the Mahalanobis distance, right? So the Mahalanobis distance is actually the first. This is fascinating. We know that a distance measure, how what constitutes a distance measure? That is, the distance has to be symmetric, it has to be non negative, and it must satisfy the triangle inequality. And after Euclid, it was this Indian in the 1930s who proposed another distance measure which would satisfy these three metric properties. And additionally, it was not a distance between points, but it was a distance between distributions. And the most fascinating part is one of his students, A. Bhattacharya, not this gentleman, N. Bhattacharya, but Amit Kumar Bhattacharya, or I've forgotten the gentleman's name, up with root of 1 minus P1, P2 as the symmetric form of what is called the Bhattacharya coefficient in the year 1941. Now, Mahalanobis is also associated with this story of predictions because his other this is another of his students in the 1960s. He studied, he made a statistical analysis of Tagore's Gitanjali. Gitanjali is Tagore's text, which got him the Nobel Prize for Literature. He tried to analyze the statistical dependency of one word on another one with regard to a very large corpus of very well written poems and sentences which were there in Tagore's Gitanjali. Now, till 2012, the idea was that the state of the art in predicting the next word was actually the same thing which is there still in our mobile phones, because it is easy. It is a simple Bayesian predictor, it is a simple statistical predictor. And this is exactly it. This technology is still there because mobile phones are not very computationally complex devices, and they would rather go in for simpler technologies which would be relatively fast. Now, what changed in 2012 was Mikolov's paper. Now, for Mikolov's paper, which essentially started with word to vec, so that brought a sea change in the way that natural language processing was looked at. In fact, I'll also look at some of the philosophical ramifications of machine learning, neural networks, why neural networks should be closer to the heart of an electrical engineer rather than a computer scientist, and how that semantic gap was bridged and is being bridged. And in some cases, electrical engineering is taking some ideas from these fledgling computer science ideas. So, what is essentially an n-gram? In an n-gram, the prediction is based on the last two or three words. The idea is I'm predicting the next word based on a vector of words which has already come in. It's a causal probability. This is essentially what an n-gram is. 2012 onwards, neural networks started getting into natural language processing. We'll see how and where. So, what is prediction in general? Prediction in general is, well, words can be predicted, and more importantly, the weather can be predicted. Okay, then financial predictions. So, there's obviously a scale of how important predictions can go. And in fact, weather prediction, if you remember, India is a force to reckon with today in the supercomputing world, because India ostensibly wanted the Cray XMP supercomputer that time for weather prediction, because as we know, India's agriculture is dependent on the monsoons, and there's that famous TRS-80 model for the monsoons. Now, they needed data for it, and they needed some statistical verification. Now, the US naturally suspected that India would use this in its nuclear program. So they refused the sale of this. But then adversity brings out the best in us Indians. And the entire set of the Param set of computers started right there and then at CDAC Pune, the Ganesh Khind area of what is now Savitribai Pune University. And well, Cray is still around, but people have almost forgotten about it. On the other hand, Param exists in many forms even today. Well, that is weather. Weather, it is extremely important. Please note that we are not talking in terms of climate prediction. Climate has a very slow rate of change. We are talking in terms of climate change today, but not weather change. So this is, of course, the old Indian philosophy of the Jad and the Chetan. The Jad is the unchanging or the slowly varying part of the world, whereas the Chetan is the rapidly varying part. So essentially, a Fourier or a frequency way to look at the world around us, what changes rapidly and what changes slowly. So one can talk in terms of knowing the weather, and as I mentioned, not the climate, knowing the market. So essentially creating a good portfolio, or what is called high frequency trading. So that is a nice thing to know. However, our aims here will still be modest. It will be knowing a language. Okay. And let us also look at what is essentially knowing a language well. What constitutes, how can I say that, well, even a human being or a machine, how can I say that that knows a language well. What does it entail? It may entail the following set of qualities. For instance, one of them, which is important to us, which we'll be talking about today, is text prediction. That is predicting the next word. And it's not just predicting the next word, the key part is the next word in context. So this context is the part of the semantics which large language models such as ChatGPT or the basic transformer framework is able to model so well. Then another application of knowing a language or knowing a concept well is essentially a question and answer. For instance, we have lots of chatbots. Like Air India actually has a very good chatbot. If you've used Air India's chatbot on its website, it's actually excellent. And in fact, most companies now have chatbots, okay, which are trained to different, of course, levels and also based on the context. Then another important application is summarization. Let's say we take a person's feed on social media such as Twitter. Okay, so is it possible to summarize the gentleman or the lady's political opinion from his or her social media posts? So summarization is also, so these are things which people are looking at in natural language processing and trying to solve these problems. Then of course one of the oldest things is machine translation. That is, given a language, is it possible to get the translation of the same, which is actually what the transformers paper of Vaswani et al. Started. And in fact, the other interesting part is this paper came out in 2017, but as of today, none of the authors are there either in Google research or Deep Brain. They've all left the company. That's fascinating. Machine translation is essentially what started research in natural language processing in the first place. And in fact, if you remember a little bit of the history, this actually started after when McCarthy introduced the term AI roundabout in the 1960s, when literally the Cold War was going on. One of the things which people in the US, especially DARPA and their Department of Defense, discovered was that there were very few people who could speak, understand, and interpret the Russian language very well. So, in fact, this is how the Cold War started literally research in machine translation. And this typically started with rule based systems. And as we know today, rule based systems do not generalize well. They are good, they are compact, they've got neat representations for the rules. Then people try to put in probabilities. But now the state of the art is deep neural networks. So, machine translation, Google Translate is decent, but then there are lots of limitations, as you and I would have seen. So, how can some of these transformer technologies get in, some of these large language models, and make these things much better? Because natural language is something which is incredibly different. Like every language does not have a genius like Panini who could encode a spoken and an active language to be very close to what computer science people today know as a context free grammar. It's incredible. So the Panini basically started off with an existing language in vogue and then codified it in the form of a proper grammar. And if one uses a language, so we will come to some of these concepts which are completely different in Paninian Sanskrit vis-a-vis what is there in transformers, what essentially is there in natural language processing for English, for instance. Okay, we will come to that. In an English statement, in an English sentence, the position of words. So, positional encoding is one of the biggest take home points from this 2017 Transformers paper. But then, as we know, in Paninian grammar, even if we interchange all the words in the sentence, the subject, the object, the verb, any POS, we completely scramble the sentence still has a beautiful, unique meaning. And the other interesting thing is poets such as Vanabhatta. Vanabhatta, their poems actually used these for some brilliant puns. And if you have read a little bit from, let's say, Vanabhatta's Kadambari, there the most fascinating part is a shift of a word, and the sentence means something completely different. And the pun here is both the original sentence and the sentence which comes by shifting one word mean are very meaningful and are completely intentional. It's really fascinating. Then there's, of course, sentiment analysis. This is also one of the things which researchers are trying nowadays. So, given some statements from a person, is it possible to characterize them as being positive, negative, or neutral? For instance, today, in today's world, people do not talk to each other that much, but then people are interacting with devices, mobile phones, computers. So, and often one expresses feelings in social media. And let's say, let's say some of the burning issues today in educational institutes, like people, young people taking their lives. So, does a person have suicidal tendencies? Is it possible to find that out from his or her social media posts? And of course, medical help also can come in another way. Nowadays, because in a country like India, wherein access to even basic medical care is extremely limited, it is, on the other hand, the penetration of mobile devices is actually very strong. So, is it possible to have a bot which human beings can confide in? So essentially, so this is in fact the Alfred Adler classification, which goes from a bot showing compassion to one level above, showing empathy, and then finally showing sympathy. Okay, so showing compassion, that is, it should not be outright rude. So the language, the natural language which is generated by the large language model, should have properties first, at least compassion, then empathy, and finally sympathy as well. So essentially, if we want a person to confide and give some details about the medical problem which he or she may have, then it is important for the large language model to have these properties. And these are topics apparently which my colleagues tell me, topics of active research. So a bot would be there to help an individual collect information, wherein this information would be passed on as and when required to a proper medical practitioner who could then help. This is the idea. Now I'll come to this basic topic. Quite a lot of this material is actually not my own. I have taken material from quite a few sources, which includes my colleagues trying to teach me this particular subject, and often failing because I still don't understand this too well. Then there are some very nice tutorials. Like there's an introduction. There's a very nice introduction which has more English and very little mathematics by Luis Serrano. So I'll try to touch some of these issues. And in fact, yeah, this is what I just mentioned. Sorry, my slides are. I actually don't have too many slides either, as you can see by the number of slides here. And I'll try to make up with some talk or bad talk. And let's see. Okay. So the idea is that the context, the n-gram technology of next word prediction in a mobile phone is definitely not according to the context. It simply predicts what word is most likely to come up after the last few, even if the sentence which is created as a result of the prediction is a completely bogus sentence or is completely grammatically incorrect. On the other hand, this problem does not happen with transformer based architectures such as ChatGPT and other large language models. So let us see some of these properties. So transformers are different because they keep track of the semantic context of what is being written. That is, there is coherence. Well, it is true that transformers suffer from some problems such as hallucination. And in fact, there's a lot. Like one of my colleagues in control theory asked a chat GPT version to describe some property in discrete time control, very, very particular property. And what came out from that was a perfectly written piece. But then when he saw in detail, the maths was completely bogus. Those equations didn't make sense, and ChatGPT had actually given quite a few references. All of them were bogus. Okay, they were incorrect. So these issues are there, and in fact, there are also other issues like, which is exactly why famous people like Jeff Hinton dissociated themselves with associations such as OpenAI. OpenAI is no longer open, and in fact, they have become the preview of a few wealthy companies which can afford that much of GPU compute power. And typically, transformers use a huge amount of training data. And one of the one of the classic examples of a transformer is, let's say, I ask it to write a story. So the input to the transformer would be write a story. Then the chat GPT agent would typically give as an output the word once. So what happens in the next iteration? In the next iteration, write a story once. So the previous input and the last output. So then the output is upon. After that, the next input is write a story once upon. The output is a. So this is how a transformer works. This is one of the things that we will try to describe in very simple language today as to how this happens. And I'll try to do this in a rather simple high school math level description. So if the next input is write a story once upon a, so the next output will be time. Similarly, write a story once upon a time there. Okay. So what is the structure of a transformer? See, I'll not go into the paper. The paper has these different blocks and connections between them, but it's often easier to understand that by just abstracting out the basic concept. Essentially, it is an encoder decoder architecture, and the encoder part has some blocks in cascade which are repeated. It is just for refinement, but any one of these blocks would have what's called a transformer block followed by a simple feed forward neural network. Let us see what this is. So if the input is write a story, the first step is tokenization. So the first step that a transformer or large language model or chat GPT does is to convert the stream of words in a natural language sentence into a stream of representative quantities called tokens. We will talk in terms of, we will see what these tokens are pretty soon. The next step after tokenization is to generate an embedding. An embedding is an encoding. We will see some artificial examples. Then we will see how ChatGPT actually does that encoding and how similar words would be, to use some rough language, be close by in semantic space. Then this is followed by positional encoding. So this is what I was talking about. Paninian Sanskrit does not have positional encoding. That is the beauty of the language. On the other hand, a language like English actually has positional encoding. We will see what positional encoding is. This is followed by, there is an attention block followed by a feed forward neural network, another attention block, another feed forward neural network. So the original transformer paper had 6 of these blocks in cascade. So this was a limitation of the compute power at that point in time. Nowadays, let's say GPT-4 has lots of these and lots of other sophistication. Finally, it is followed by what most of us are familiar with, a softmax. Softmax essentially is for a neural network with, let's say, a K class classifier. So typically one has the activation function at the output neurons to be the softmax. So it essentially raises something to an exponential and normalizes it. We will see why and how softmax becomes crucial for transformers. So after the softmax, the output is ones. So after the softmax, because these are normalized, so the results are numbers between 0 and 1. Essentially, any number in that range can be interpreted to be a probability. And what ChatGPT does is, for all the words in the dictionary, it assigns a probability to it, and its output is just the one with the maximum probability. Okay, that's as simple as that. Let's now see what these different stages of a transformer are. The first is called tokenization. The computer science community is well familiar with what tokens are. For instance, anybody who's taken a course in compiler design would know what these tokens are. The idea is that a large language model or a transformer takes every word, prefix, suffix, punctuation mark, whatever, and converts that into a known word from a library, which is going to be a token. And of course, here, one of the things which people ask is, can I not have an LLM for, let's say, some of the Indian languages? We have 22 languages which are national languages, and the number of dialects is actually more than 8 bits. So, so it's actually more than 256 in India. So is it possible to have, is it worthwhile even having a large language model for, let's say, a low resource language, a low resource regional language, which doesn't have that much of, there are not too many data sets to experiment on? Well, there are two answers to this. There is one line of thought which says yes, we should. The other line of thought says no, it isn't really worth reinventing the wheel. We are better off trying to get more technology into it. Well, these are domain specific as well. So the interesting part is, the moment this transformer paper came about, people in image processing and video processing, they discovered that this concept comes very naturally to signal processing, image processing, and video processing. So the research started in vision transformers. So it is essentially domain specific. Then there is a vivid video vision transformer, so on and so forth. And there's a lot of training. So the training almost is all sentences on the internet today, okay, or a very large corpus. So with the training, it learns the structure of sentences, and for images and video, it learns their structure. So it is, of course, domain specific. So if the input, so coming back to tokens, if the input is write a story followed by a full stop, then the idea is that this, every one of these entities is converted into a token. It is somewhat like lexical analysis. For instance, if we have a compiler for a C-like programming language, there is a keyword called for. How does that? So I can have a finite state machine. So in a compiler, this is typically, computer science people don't believe it, but it's actually a Moore machine or a Mealy machine, because there is an output. It is a class of finite state machine models with output. So it's a Moore or a Mealy machine, wherein it comes here and what is a accepting state in a DFA actually becomes a Moore machine whose output is a token or an identifier. That identifier could be a number, okay, corresponding to the keyword for, which is output by the lexical analyzer part of the parser. Okay, so if I have something like this, then I can break this into these different blocks, wherein if I see I, N, and T, this would correspond to a token which indicates the data type integer, and these two are variables. Okay, so whatever is a token in compilers, this is exactly what we are talking about here. It's a representation. Then of course a little bit of philosophy, wherein one studies the electrical engineering and the computer science conundrum. Electrical engineering actually has given a lot to computer science. The basic Richard Bellman's discrete time control of the 1940s, wherein he wanted to impress the Navy with some hefty terms. So he called it dynamic programming. Now, in the 1960s, computer scientists took over and almost the entire field of dynamic programming. From discrete time control, they borrowed it into computer science. Graphs, what started as an abstract entity like the Kenningsburg bridges problem. So there's this town of Kenningsburg in Germany, which had lots of bridges. So all of these problems, which now generalize to the traveling salesperson problem, essentially says that is it possible to have a tour which makes me cross all these bridges in this particular town? Electrical engineers took over by looking at planar circuits. So in designing PCBs, jumpers are almost a no-no. So the idea is, given a circuit, is it possible to find out whether the circuit is planar or not? In the 1960s, there were researchers such as Norman Balbanian, Sundaram Seshu. In fact, there's a very famous book on circuit theory wherein the graph theory part of circuits is described. This is, I think, a 1965 book by Balbanian and Seshu. Then automata theory, the fact that, let's say, a lexical analyzer, whatever it does in abstract software, in a compiler, can actually be fully implemented on a breadboard using flip-flops. This is fascinating. So automata theory actually comes from flip-flops. On the other hand, natural language processing in computer science has also given us some very interesting things. It actually started with latent semantic analysis, probabilistic latent semantic analysis, then latent Dirichlet allocation, and today, of course, transformers. The idea in LSA or PLSA was essentially, if I look at, let's say, I've got a web page, and these are the latent variable methods. So can I categorize that web page into, let's say, sports, or let's say it involves politics, or let's say something involves both? So what computer scientists looked at was essentially the structure of the singular value decomposition of a matrix. So these singular values would correspond to latent topics. So they had a slightly non-mathematical interpretation of the singular value decomposition. By the way, the singular value decomposition is not a very old algorithm. It is a 1953. The way that we know it today is due to Swedish mathematician Beerhammer. Beerhammer's paper came in 1953. It is as recent as that. The CSWE sort of continuum in a way can be described as CS looks at categorical entities, coarse grained. CS is coarse grained, whereas EE is fine grained. The level of quantization is much more. For instance, computer science looks at characters constituting a string. And what can I do with strings? Let's say I've got a DNA string, I can do string matching. Whether there is, so a particular character can match or need not match. Electrical engineering, on the other hand, interprets this as signals and looks at correlation between two signals. So the essential idea is that even the computational complexity, it is very natural that they are actually quite similar, apart from the fact that the CS world considers a much simpler case wherein there is a match or there is no match or there is a match with some errors, which essentially is a dynamic programming solution. On the other hand, with correlation, one looks at the degree of match. And in fact, today, for neural networks, the basic idea, we call them convolutional neural networks, but there could be nothing which is farther from the truth. It is a complete oxymoron because the fundamental operation is actually correlation. It's not convolution at all. And it's not a neural network, but an artificial neural network. Now, in terms of, well, so the CS world, so how would a CS world look at words in a dictionary? Let's say I I were a teenager who's interested in fast food. That's all that I eat. Well, that's also true for me. Unfortunately, that's what people at home tell me. So let's say my world of food is pizza, burger, and let's say a sandwich. Okay. So if this is my world, then I could encode this world using what is called one hot encoding. So pizza may become 100, then a burger might become 010, and a sandwich may become 001. So this is a traditional computer science way to assign numerical values to what are categorical entities. Now, this works relatively fine. In fact, it is easy to understand things like recurrent neural networks, LSTMs, or bi LSTMs using one hot encoding and using how the context of words in a sentence can be found out. It is perfectly possible to do so. However, the important part is that people discovered it does not scale well. One hot encoding, electrical engineers might interpret as something like a Johnson counter. A Johnson counter has exactly one bit that goes from this end to that end. Okay. So it in fact has an exponential size as compared to the actual binary number which is inside. So this obviously does not scale well. On the other hand, in transformers, we find that similar words occupy similar parts of semantic space. How does this happen? So let's take a very simple example. So we'll take a couple of handcrafted examples. This is just to illustrate the concept. Now suppose I've just got two concepts. So let's say I've got I've got some words. Let's say calf, I've got puppy, I've got dog. Now, where would cow go? It's actually intuitive that cow would come here. Why? See, this is a handcrafted example because these two axes the x-axis could represent age. So puppy is young, a doggy is a bit mature, and the other could be size. Okay, a calf on an average would be bigger than a puppy. So a cow would come here. So now what we observe is that a word has a semantic space. Okay, it's got features and words are close to each other. Words have relations between them and words could be far from each other as well. So if I look at it in just a two-dimensional space, so puppy has low age and low size, calf has low age but relatively large size, a doggy has it's a medium age, but the size is low. And a cow, what we are looking for, has high age and high size. So what we need, so this two-dimensional space, so all of these concepts in this completely handcrafted example are in two-dimensional space. Okay, these are called embeddings. They essentially capture analogies or relations. Let's take another example. Another example is that of what I'm accused of doing most of the while on the screen. Okay, so let's say suppose we've got movies such as You've Got Mail. So this is that Tom Hanks movie. Then there's Rush Hour, the crazy action and fun movie. There's Rush Hour 2. Then there's a movie Taken. Now, once again, this is a handcrafted example, human interpretable example, because if it is not that, then we need some form of distance measure. We'll see how ChatGPT does it. It's actually fascinating. And it's not very, sometimes not that trivial to understand. So let's say in this semantic space, we've got for movies, we've got action on one axis and we have got comedy on another axis. So with regard to that, you've got male has got zero action, but is scores pretty high on the comedy scale. Rush Hour has a lot of action and a reasonable amount of comedy. Rush Hour 2, which came after that, has even more action, but this is actually a rather subtle example. The comedy, the jokes become PJs, the jokes become pretty poor. So it scores a bit less in terms of the comedy part. Taken, on the other hand, is all action and no comedy. So what do we get? We have got an embedding now for movies. So now movies can be represented in two-dimensional space with two coordinates. This is the idea. Now, this is where transformers come in. This is positional encoding, and this is where the English language, and for that matter, almost all natural languages differ from Paninian Sanskrit. We'll see why and where. The idea is that each token, so each word, I'm using these two terms interchangeably. I'm using the terms word and token interchangeably. Now, each token is represented as a vector of numbers that are determined somehow. In these synthetic examples, the way that we have seen is we looked at, let's say, the age and size. Then we look, then we looked at action and comedy in two-dimensional space. Now, the way ChatGPT does is it starts from random initializations. It trains over almost all the sentences that are there in the internet. And what it does is it removes a word, then tries to predict a word. So this is the optimization problem that the deep neural network in the transformer tries to solve and tries to find a solution which is fairly optimal. So given the amount of training that a transformer goes through, even with fairly random initializations, one actually comes to the same set of vectors which encodes a particular concept or a particular word. By word here we mean a token. Okay, this is the way that chat gpt does it. Sorry, I don't have slides for that, but I'll just try to speak. Let's take another synthetic example. Let's say we have an axis called tech, and we have another axis called fruitness. Okay, it will be clear. This is Serrano's example. So let's say an orange, let's say, has coordinates 0 comma 3. So it is a fruit, right? And apparently growing an orange is low tech work. On the other hand, a cherry apparently needs a little bit of technology. So cherry has coordinates here 1 comma 4. On the other hand, a mobile phone has coordinates, let's say 3 comma 0. There is no fruitness here. The trouble is there could be words which are ambiguous. Okay, so this is the example that I took. Orange is 0 comma 3, cherry is 1 comma 4, phone is 3 comma 0. But what about ambiguous words? For instance, I could be talking in terms of a tasty apple. Now, we human beings know that it is the context, tasty and apple, which indicate that I'm talking of apple as a fruit. On the other hand, if I say something like a dependable apple, then I'm possibly referring to an apple as either an iPhone or iPad or let's say a MacBook. I'm looking at that. So this is the interesting part. An ambiguous word, depending on the context, would have more than one encoding or embedding associated with it. Okay, And the training part, in the training part itself, the ambiguity would be resolved based on examples, common examples of different contexts in which they have been used. Let's see an example. So, in fact, here for that write a story example, let's say this is an encoding. Okay, the Transformers paper started off with 512 level encodings. That's just a number, and in fact, they had little tricks to break it down into 64, 16, 64, so on and so forth. 2 to the power 4. So write a. So a has an encoding. These are fixed length encodings, by the way. Okay. Let's assume that these are vectors of size 10. There could be positive numbers, negative numbers, greater than 1, less than 1, so on and so forth. Write a story. So every one of these words would correspond to tokens, which would have a vector representation. And I've just given an example of how ChatGPT generates those representations. Similarly, the full stop would have another representation here. We'll take completely handcrafted examples. A sentence, let's say, write a story, full stop, is also a vector, wherein every word is a vector. And in fact, the interesting part is that if the length, if the feature length of a vector is long enough, I can, for instance, take a sentence to be also a vector of the same length. But then let's say I'm taking only the important components there. All right. So let's make an attempt to understand what positional encoding is. So suppose I've got two vectors in this fruitness and tech, these two axes, and I want to add them component wise. That's one way to get a sentence out of two words, right? I simply add the corresponding components. The resultant is 4, 6. Now we also realize that there is an issue because addition is commutative. For instance, if I had 3, 4, and then I'm adding it to 1 and 2, I'm still going to get 4 and 6. The example is I'm not sad, I'm happy, and I'm not happy, I'm sad. So these two sentences have completely different meanings. On the other hand, they have the same words. Both these sentences have the same words. Their positions are different. Now, the idea is we need to encode these words in terms of their positions. So, addition, in order to get an encoding for a word, for a sentence in terms of its words, doesn't work. The semantics is lost. That is, two sentences with different meanings should essentially give two different vectors. Now, one possible solution is what the Transformers paper considers as positional encoding. Now, this is not something that is completely an alien concept to us. Why? It's like, for instance, very simple. Whether one is an electrical engineer or a computer scientist, one knows about a decimal value of a binary number. Every bit has a position. So this is position 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3. So the encoding of this binary number, its value, is unique. So that means there is a positional encoding for each bit. Another example, which is familiar to those in computer science as well as electrical engineers. Electrical engineers like to look at, let's say, a tree of wavelet coefficients. Okay. In this case, for computer science, it's much simpler. Let's say there is a binary tree, and let's say I start my indexing at I equal to 0. So the left child of that binary tree is always at 2i plus 1 if I have an array implementation, and the right child will be at 2i plus 2. And if the tree is skewed, then obviously I'm going to be wasting a lot of space. But the important point is I have a unique positional encoding of the nodes in this tree. Okay. If it's balanced, it's pretty good. Now, the next concept in transformers is that of attention. Now, what is attention? The Transformers paper talks in terms of scaled dot product attention. So let's look at these terms one by one. Scaled, let's take the scaled part away. In fact, what is a heuristic in the transformers paper actually has some solid theory behind it. We'll talk in terms of that. The attention in a way clarifies the context. That is, words which are closer in feature space are likely to be actually close in terms of the distance as well, let's take examples. So let's look at the word bank. Now this also says that one word could have more than one encoding, and this is one of the important concepts in a transformer. That is, one particular word may be associated with more than one encoding. Like the word bank, I could talk of the bank of a river. In this case, during the training, the encodings for this bank and the encoding for river would move close in feature space. We'll take a full example for this. Money in the bank. So in this case, bank and money would move close. The bank of a road, you know that roads are sometimes tilted so that vehicles which take a turn at a high speed don't really go off. You would have seen roads banked on. I first saw them in highways in Maharashtra, Kerala. Kerala has got some lovely roads, and all of them are banked. It's actually pretty interesting. There's a proper speed limit for that bank, above which they don't guarantee that your vehicle is going to go tangentially. So in this case, the words bank and road move close. We'll take a full example. So in each of these sentences, the word bank carries information of the neighboring words, which essentially sets the context and the encoding. Another example is tiger in the green woods. So this sentence may be closer to the heart of an environmentalist. Okay. Or tiger woods in the green. This sentence would be closer to the heart of a golf enthusiast. Then, of course, I talked in terms of tasty apple and, let's say, dependable apple. This is a concept in a transformer, multi-head attention. That is, many different encodings are used to modify vectors and add context to them. So now let's look at what happens in a transformer, rather how in a transformer the next word prediction happened. That is, what is the role of the feed-forward neural network? What is the role of the softmax? So this feed-forward neural network predicts the next word, and softmax converts that score into a probability. How does that happen? Let's say write a story. After that, what was the output of the transformer? It was once. So write a story. This is split into tokens. Then there are embeddings. Positional encoding is done. After that, all the words in the dictionary have a probability associated with them through a softmax. This is what I had described earlier on. So all the words in a dictionary, starting from aardvark. Aardvark is one of the first few words in the English dictionary. It's in fact an animal with a very long nose. In fact, the F-111 fighter bomber of the US Air Force was actually called aardvark because it had a long nose. So the words in a dictionary range from aardvark to, let's say, zygote, ZY. This is lexicographic ordering in the dictionary. And here, the output of the softmax results in probabilities. And the word once has the highest probability, 0.5 in this example. So the output of the transformer is once. Okay, write a story, the transformer outputs once. It could have been something else also there or somewhere. In fact, there are some lighter models of a transformer wherein one can actually examine the second highest probability and look at what were the words which correspond to the second highest probability, third highest probability, and actually it's instructive often to go through these. Okay, there's something else also. There are lots of these properties of transformers which are much like human beings. It's like saying that I've got a set of examinations in school. I have to appear for my exam in history, I have to appear for an exam in civics, I have to appear for an exam in physics, in chemistry, in maths, English, so on and so forth. My training is, if I'm trained well, I will I will prepare my subjects either in order of preference, or let's say I prepare equally well for all of those. However, on the day of the examination, so if the examination is a history exam, I'm definitely not going to cram up my maths formulae. Okay, before the exam, I'm definitely going to learn what is important for the context in which I'm going to use this. So this is something which is called post training. Why? For instance, if I have a large language model, I have trained it. Now, if I want to use it for a chatbot application, I will need to have a post training phase where it is trained on large data sets of conversations. On the other hand, I might have a large language model which helps to write stories or poems, or if you're a teacher like me, even code. Right? Students nowadays deposit chat GPT written code. And if you run it, if the model is sufficiently different, there's enough diversity that the next time you ask it to write a piece of code, the output will be somewhat different. Fascinating, huh? Scary also. Why? the, suppose, let's say, the internet is actually a very poor repository of things to learn, because suppose the question is what is the capital of Algeria. Now the internet document which had that possibly had the next sentence after what is the capital of Algeria as what is the population of Algeria, or let's say what is the capital of Burkina Faso. So the idea is that it simply mimics what it has learned. That is the idea. Now, post training is that there is general training, and after that, it is again trained on a large corpus of, this is the key part, application specific. Let's say if I want a chatbot, then the post training has to be on a large number of question and answer data sets. That's the idea. So there is obviously a little bias towards the last things which are learned. Now let's pay a little bit of attention to attention. What are these things? Once again, let's take that fruitness and the tech example. We have an orange at 0, 3. We have a cherry at 1, 4. We have a mobile phone at 3, 0. Now, the important point to realize is that a dot product, this is what transformers, the transformers papers took. The dot product is a measure of how close two words or two tokens or two concepts are. Similarity. Let's say for these as our coordinates, if I take the dot product of cherry with orange, I'm going to get 12. 1 into 0 plus 4 into 3. Cherry with a phone would give a small number. Okay, 1 into 3 plus 4 into 0. And orange with a phone is going to give me an even smaller number. These two are, look here, 0, 3 and 3, 0. I could extend this idea also to angles, but then I like to look at the cos of the angle between them. But then I also realize that the dot product actually corresponds to the cosine of the angle if I'm on the unit circle, if I normalize my vectors. So whether I take a dot product or whether I look at the angle, I'm essentially looking at the same thing. Now, why does the transformers paper talk in terms of a scaled dot product? This is a variant of a dot product. What is scaling and why is this important? The heuristic in the scaled dot product attention is that we divide by the square root of the length of the vector. This is actually very intuitive, saying that if I've got very long vectors, let's say vectors of size 512, then it is very easy for a dot product to actually really blow up. It might, so the finite word length affects what electrical engineers study in digital signal processing actually come into, so there might be overflow issues. Because of that, the heuristic of dividing by the square root of the vector length actually works well in practice. And this is, in fact, this has some solid theory behind it. If you have looked up Guimero Navarro's paper on the normalized string edit distance problem, I think he has two CSEM papers. It's actually pretty instructive to read them and see that this heuristic has actually some sound theory behind it. So cherry dot orange would simply not be the dot product, but will normalize this by the length of the string, which is under root of 2. Cherry dot phone, it's going to be 2.12, and orange dot phone is going to be 0 anyway. So now let's look at a situation wherein we now have representations for orange, phone, cherry. But what about apple? So apple would start off with an ambiguous representation. Let's say both the apple company as well as the apple fruit would map onto coordinates. Let's say this is a completely synthetic example, 2, 2. Now let's say we append another axis for general connector words like a, an, and, so on and so forth. And let's say in our example, we take these numerical values. So we have taken another axis and arbitrarily assigned and, the token for and, to have value of 002, 00, and then 2. And similarly, and to have 003. So what is this attention? So what we do is we look at a sentence. We look at essentially first, we look at the matrix between them and look at what these distances are, or normalized dot products. Okay. Obviously, this is going to be symmetric, right? Now, if the sentence is an apple and an orange, how would these values change? The idea take those rows, we take those and then make those changes. How do we do that? So an orange and an apple, or an apple and an orange, if we had no positional encoding. So orange now becomes 1 into orange plus 1 into orange plus 0.71 into apple plus 0 into and plus 0 into and. Similarly, apple becomes 0.71 into orange here plus 1 into apple, phone is not there, 0 into and 0 into an. Similarly for and. If the sentence is an apple phone, how do these numbers change? Now in this case, phone becomes 1 into phone plus 0.71 into apple plus 0 into and. Similarly for apple, similarly for and. So every sentence, now these numbers change. There is a need for normalization. Why? Because these numbers could blow up. So one normalization is simply to take the coefficients to add up to 1. So an orange normalized would be 1 into orange plus 0.71 into apple divided by 1 plus 0.71. So this gives reasonable values here. So this, by the way, this is something that we studied in school as the division of a line in the ratio of m is to n, or k is to 1. Suppose we had an example wherein the two base words were orange and bike. And remember, these coefficients could also be negative. We try to normalize them. What do we get? Unmitigated disaster. That's trouble. This is where we realize that coefficients should be positive and they should respect order. Softmax comes to the rescue here. So instead of x, we transform this to e to the power x. So basically orange now becomes, instead of 1 into orange plus 0.71 into apple, becomes e to the power 1 into orange plus e to the power 0.71 into apple, and so on and so forth. So the coefficients are positive, it respects order. Similarly, if we had that bike example, that -1 now becomes e to the power -1. So we get some reasonable values out here. With softmax, well, I'll just quickly give the results because I'm also running out of time. So this is what I get. With softmax, an Apple phone results in the following numbers. Now, Softmax has a problem, that is 0 doesn't map onto 0 because 0 maps onto e to the power 0, which is 1. So this is what the mapping is. So an orange becomes zero point 0.4 times orange plus 0.3 times apple plus 0.15 times and plus 1.15 times and. Now suppose we make a 0 mapping to a 0, that is, we remove these as a gross approximation. Then these are the coordinates which would come. So an apple and an orange, we're talking about fruits. So the coordinates of an apple now become 1.14 and 2.43 in our example. For a sentence, an apple phone, the coordinates of an apple, sorry, there's a typographical, no, this is okay. This is okay because the phone comes here. The coordinates change. Let's represent this graphically. The ambiguous concept of apple was here. Now, with this, these two concepts tend to move away now based on the context. This is the importance of the scaled dot product. Okay, so I guess there's very little time. I'll put a little disclaimer here, some closing notes, a little bit of a warning. So I've talked in terms of, I've actually taken lots of shortcuts. Okay, this is what we call the Pythagoras method. Instead of going like this, I've taken lots and lots of shortcuts. I've made lots of assumptions and I haven't given too many details. Transformers is a pretty tough concept, and this in fact describes it. So Transformers isn't stressful at all, says Josh, who's only 25 years old. Right? So it's that tough. And then I'll possibly end with a little example. So I'm talking to the insurance company. I hit an animal. So, like, what is the insurance that you've actually learned something from whatever I've talked about today? So it's something like, I say I hit an animal. Am I covered? So the insurance agency asks, what did you hit? So my reply is a fish, because this is what has actually happened. So please don't take my word for it. There are lots of very nice tutorials on the internet. I'm also going through quite a few of them myself, trying to learn more. And also, please refer to the original paper also. It is not very readable. Okay, it is written, but then it's also written from the point of view of an engineer, experimenting with some of these concepts and then looking at how these come about. So, for some reason, my camera has stopped working. Sorry. I hope I'm audible, or has it actually?
No, no, you are audible, sir.
Okay, okay. So now my camera has gone conk. Okay, so I guess I'll stop speaking. I've spoken quite a lot, and yeah, maybe Chairperson Madam, you can open the floor to questions. I think I've basically, it's also logged me out.
Yeah,
I'll
but we,
try
yeah,
to, I'll try the computer science solution. You know what that is, right? Switch.
yeah, reboot. So thank you, Professor Roy. Transformers, as you said, is tough, but you like made it so simple for all the participants here. So I'm opening the floor to the participants in case they want to ask Professor Roy uh, any questions or anything that was not clear to them.
Yeah, I think now things are working. So the computer science solution works.
Yes. So, and as expected, your talk was like full with hilarious snippets. Like, so,
जब असली चीज मालूम नहीं होता तब इधर उधर की बातें करनी
acha, acha, ठीक है.
होती.
So, participants, in case you have any questions for Professor Roy.
Yeah, please feel free to ask, because that's what is exactly going to tell me what I don't know, and it will help me learn that part also.
So anyone, please raise your hand or you can unmute yourself also. Uh, Dr. Banerjee, the attendance is being monitored and the feedback is going to be at the end of the FDP. So we don't have any feedback link for each session. Yeah. Any question for Professor Roy?
Good evening, sir. Sir, can you summarize the importance of the positional encoding once again, despite that we have got encodings through the data available, like say word2vec and the globe kind of the
Okay,
encodings
okay.
available.
See, I'm
Yeah.
Dr. Goel. I don't work in this area, so I actually do not know much about the nitty-gritty details of word2vec, or let's say how a blue score comes, or all of that. I actually don't have much idea, but the idea of positional encoding is essentially that sentence: I'm not sad, I'm happy, and I'm not happy, I'm sad. So these two actually mean completely different entities, although the words are the same. On the other hand, in a language like Sanskrit, I would essentially, it wouldn't matter. So Ramah Vidyalayam Gachati, or Gachati Vidyalayam Ramah, or Vidyalayam Ramah Gachati. I interchange the subject, the object, the verb. Essentially, this is the beauty of Paninian grammar. There is there is no need for positional encoding because the sentence is makes perfect sense. Okay. On the other hand, in these examples, I'm not sad, I'm happy, and I'm not happy, I'm sad. This is in natural language, and yeah. So, Dr. Parnami, I'll try to share I'll try to share these slides. They're actually pretty large to send over the internet, so I'll put it on maybe Google Drive and then share it with Preeti madam. Okay, but please, just also a request, because I've taken these, some of these concepts are not very original concepts. Okay, I've taken these from the internet, so please don't put them on a public platform, or use it for your own own benefit. Okay, so that is just a request. All right, so do you get the idea of positional encoding? That's it. That is, it's not just the words which are there in the sentence, but where a particular word is in a sentence. It's something like the binary number example that I gave, 1001, wherein every bit has a positional encoding. So the concept of a MSB and a LSB actually comes because of the positional encoding. हर बिट की अहमियत अलग है, वो कहाँ पे है बाइनरी नंबर के अंदर, उससे पता चलता है. Okay,
Yes,
so every
yes,
bit has its importance. That is the idea. So it has positional encoding.
yes,
Is it
yeah.
up,
I
Roy?
understood the thing. Yeah, yeah.
Okay, thank you.
Thank you so much.
So thank you for joining, Professor Roy. We are very happy you could make it, and this session was very informative and useful for the participants. So
Thank you very much. Thank you very much for the honor. And anything that you organize, I think we all, those of us who have attended events organized by Preeti Madam, know it actually quite well that Preeti Madam organizes these beautifully.
thank you.
Thank you very much once.
I think there are a couple of two raised hands more, Dr. Reena and Dr. Dipanshu. If you could just take quick questions from them
Yeah, yeah,
also.
yeah. Can you just
Yes.
unmute your microphone, because I
Yes.
actually have a very old computer, and there was something like TF-IDF. TF-IDF in a way actually does that encoding. Okay, one of Preeti Madam's colleagues, Dr. Bansal, has had experimented with
Yes.
TF-IDF when that was a very fresh concept, and it's actually fascinating. But the idea essentially is whatever way one is looking at it. So even a two-dimensional data structure like a tree can have positional encoding. It's not just a sentence. All right. So
Yeah.
there are numerous examples of positional encoding everywhere. Yeah. Anybody else?
Roy
Just
sir,
unmute your microphone.
Roy sir,
Yeah.
good evening.
Good evening, Dr. Reena.
I had many times I found that in your lecture you have many times mentioned electrical engineer.
Yeah.
So did you find the similarities between the transformer in computer science and transformers in electrical?
I actually, madam, frankly, if I were to talk from a even naughtier point of view, I found more similarities with Optimus Prime and Bumblebee, that movie series Transformers, than actually this. No, there's actually, that's what I mentioned. That is, the word basically came from, it was designed for it was designed for sequence to sequence translation. So it
Yes,
would
yes,
transform, let's say, a sentence in German to another sentence in English, possibly with a different number of words in each. So it's not a only word to word. So there is a concept of a context. So that transformation actually got them the name. But then these are often weird stories. Like, why is the programming language like Java named like that? See, Java is a slang for coffee, and the person who actually gave a push to a new programming language was thinking of a name for that programming language, and there was a cup of coffee on the window, so he called it Java. So that is in fact, as the Sun Microsystems, that icon is actually a cup of coffee. Then the programming language C, how did it get its name? Brian Kernighan, that time they were looking at programming languages. One of them was called B. The next one was actually called C. Okay, so that these names are fascinating. Many of
yes,
them have actually not come through very logical ways. But for a transformer, it's actually, let's say, sequence to sequence or sentence to sentence transformation.
yes. Because many times I search for the fusion of transformers. I'm working at that level. So
Yeah,
for the
yeah.
action or for the translation, I'm working on the fusion of
Wow.
transformers. So many time it gives me the images for actual electrical transformer fusions. So I asked the same question for that.
Okay. Yeah, it's
So
actually interesting.
many of the
See,
things I couldn't understand from because I'm not from the electrical background. So I wanted to just ask, is there any kind of fusion of transformer in electrical engineering also?
madam, I'm also not an electrical engineer. I'm a complete fraud. In fact, unlike people like Preeti Madam, who essentially have that Midas touch. So King
Okay.
Midas, whatever he touched turned into gold. In my case, I'm a complete fraud. I, I'm trained as a computer scientist, but then I have always been what is called in the chaste vernacular, मैं बचपन से सरफिरा रहा हूँ. So if somebody tells me to go in this direction, I would go in the opposite direction. I'm a logical, or a rather a illogical not gate. So, like, after I completed my PhD, people said, "Oh my God, this is the area of information technology. You should go into computer science." So immediately something started working in my brain. I went in the other direction. I thought that now let me try to wear a mask, not that N95 one, but mask of an electrical engineer. So my first job was in an electrical department at IIT Bombay. I was in a communication group without knowing head or tail of communication. Then it's said that once a tiger tastes human blood, okay, एक बार वो इंसानी खून को चख लेता है, जिंदगी भर के लिए आदमखोर बन जाता है. So moment a tiger tastes human blood, the tiger becomes a man eater for life. So my second job
Yes.
was also in a has also been in an electrical engineering department. But it's
Right.
actually a very nice learning experience.
Yes, yes, sir.
Trying to
Rightly said.
teach, trying to teach some very basic courses in electrical engineering also. It's actually been a nice learning experience. It's not very tangible. Okay, it wastes a lot of time, but then as long as one learns new things, one is happy.
Rightly said, sir. Thank you so much.
Okay, thank you, ma'am.
The participants have sent many thank you messages to you and everyone is saying it was a very nice, informative session.
Thank
Thank you
you.
once again, Professor Roy.
Okay, madam.
Okay, bye bye.
इजाजत दीजिए.
Namaste, sir.
Good night.
Namaste, sir.
Good night.
Okay, sir.
Bye. Thank you.
Okay, sir.
Thank you, sir. Good night.
Okay, participants, our next speaker is Dr. Abhishek Sharma from LNMIIT, and he has joined us. Dr. Abhishek, you are there?
Hello,
Yes,
am I
so
audible?
yes, you are audible. Hi, hello, Dr. Abhishek, how are you? So
I'm
I
doing
will
good, thank you.
request Dr. Nikunj to introduce you to the participants.
Okay.
Yeah, Dr. Nikunj.
Yes,
Yeah.
madam. Yes, just a moment. Let me share the screen over here. Okay. Okay. So, ma'am, is it visible?
Yeah, yeah.
Okay. Thank you, sir. Okay. Good evening, everyone. So, I'm Nikunja Kara. So, it gives me immense pleasure to welcome you all to the second session of this ATAL FDP. Your enthusiastic participation truly reflects the importance of this emerging field. For this session, we have with us Dr. Abhishek Sharma, who will be speaking on the topic low power devices for deep learning. So let me introduce the speaker. So Abhishek Sharma received his B in Electronics Engineering from GYE University Gwalior, India, and PhD in Engineering from University of Genoa, Italy. He is presently working as an associate professor in the Department of Electronics and Communication Engineering and adjunct faculty in Department of Computer and Communication Engineering at the LNM Institute of Information Technology, Jaipur, Rajasthan, India. He is also a member of IEEE, Computer Society, and Consumer Electronics Society, a lifetime member of Indian Society for Technical Education, a lifetime member of Advanced Computing Society India, and a life member of Computer Society of India. He is also the coordinator of the ARM University Partner Program, Texas Instruments Lab, and Intel Intelligent Lab in the present institute. He is also the center lead of LNMIIT Center of Smart Technology. His research interests are real-time system and embedded system. I now invite Dr. Abhishek Sharma to take over and begin the session. Thank you.
Okay, so let me share you my screen. Is it possible share?
Okay, so let me stop sharing from here, sir.
Okay, allow
Now
share
you can
screen.
able to share. Yes.
Okay, so I think
Dr. Abhishek, before you start, I think there is a raised hand from Dr. Megha. Can I just take a quick question, Dr.
yeah,
Megha?
yeah, of course, of course. Yeah.
Uh, Dr. Megha, is there any question, any concern? All right, Dr. Abhishek, you can begin, please.
Okay, allow to share the window or screen. I don't know which one is good. Okay, screen. No, just a second, One
Okay, sir.
second. Last 1 minute. Okay, share the window. Is it visible now? My
Mm,
screen.
uh,
Yes,
I think
it's,
it will going to
yeah,
take a
yes.
couple of
Yes,
seconds.
sir,
Yes.
it
Now
is
now it
visible.
is visible.
Yes,
Yes.
it's visible, Dr. Abhishek.
Okay, can you see my face also as well? Am I
Yes.
No.
visible?
Yes. Yes.
Yeah, both of them are visible.
uh,
So
yes.
I can
Yes.
only see my presentation. I can't see any comment at the moment. So if you have any comment, don't raise the hand, just ask. Okay.
Okay.
Okay, so let me start. The topic is low power device for deep learning and deep learning for low power devices. Basically, what we are going to discuss in this presentation is associated with what is AI and how hardware is can be introduced to run sometimes or to design a AI oriented chip or AI oriented program or something similar. So we are not what we are going to cover is that we are going to cover few basics and then we move to different kind of low power devices. For example, we will go to FPGAs, we will go to microcontroller, will see what are the firmwares, what are how.
Sir, sorry to interrupt you. Sir, have you shared any PPT or
Yeah,
something?
yeah, already.
But
But
the
now,
PPT is not visible to us, I guess. Please check it from your end.
I think my screen is visible. Is it so or no?
Yes, your screen is visible, but PPT is not visible
I'm sharing
at the
my
time.
my screen. Is it visible?
Yes, the screen is visible, but the PPT
think,
is not
Dr.
visible to
Abhishek,
us.
if you just go to the PPT, if you just
Okay.
go to the
Yes,
PPT
yes.
and
Go to the PPT, please.
I'm
yeah,
on PPT.
okay, you just, I think, stop sharing and start again. Share the full screen. Uh,
Okay.
Yeah, share the full screen rather than sharing a window. Yeah,
Okay. Okay. Stop. Share the
and
screen.
yeah,
And now what is it visible? The screen is visible?
just maybe give us a say minute.
Yeah, yeah, take your time.
Yes, yes,
Yes.
now it's
Now it
Huh?
visible.
is. Is it visible?
Yes.
Okay.
Yes,
So
yes.
let me start again. My name is Abhishek Sharma, and the introduction is already given to all of you. Now, let me start with the topic. The topic is deep learning for low power devices. So basically, it is low power devices for deep learning. So basically, what we are going to cover is the hardware component to run deep learning algorithms. How can we do that, and can we design such hardware which is already intelligent? Both kind of things. Okay. So in outline, what we are going to cover is basically the introduction. What is AI? The key factors, examples of deep learning, machine learning, and AI. Apart from that, what we are going to cover is some basic models which we are going to deploy on a hardware. Apart from that, we will see some framework. For example, Simsys NN is a very important framework. Apart from that, we have SNN spiking neural network, which we run on the similar hardware. Then we will see whether how we can run a deep learning algorithm on a microcontroller, and then we'll see whether it is possible to design a intelligent hardware using FPGA. We will see all these things with the help of certain a case study we are going to cover with sign language converter. Basically, in this, what is going to happen is we are going to convert the sign gestures into words and a sentence. Okay, so and at the end of the presentation, I'll show you some demo work which we have done in our lab related to this topic. Okay, and if you have any doubt, any question, you can always, interrupt me or ask the question. Okay, let me start. What is AI? AI is basically artificial intelligence, which is a full form, and what it covers is any technique that enables computer to intimate function of intimate. Basically what it does is it does two things: it solve problem and act rationally. So it is an application which is intelligent. When I say intelligence, it means it can act according to the requirement, and it can take care of certain important tasks. What are the AI principles associated with artificial intelligence? Principle associated with this is reasoning, understanding, cognitive ability. Apart from that, it can generate information and also display the knowledge and facts accordingly. What are goals associated with AI? The goals which are associated with AI is to build systems that exhibit intelligent behavior. Apart from them, it helps in understanding intelligence in order to the model which is being deployed to it. Okay. Why? Okay. What are the key factors associated with it? So we can see that there's a ABCD model. So A stands for algorithm. In the algorithm, what we'll see that there are deep learning algorithms which are associated with generation of AI, and then there's a business opportunities associated with the scenarios and the values related to the AI product. Finally, what we can see is that there's a data which has been used or utilized to do certain level of analysis and prediction, and then there's a component called C or chip, in which what we do is basically because of artificial intelligence, there's a demand for the chips similar which can do multiple like parallel processing, TPUs, FPUs are much more on demand, and nowadays the demand is more than TPU and GPUs. It is more about the intelligent hardware. Okay, what are the sectors in which AI can be implemented? So we can see now there's no sector left almost. We can see there's an AI implementation of AI in healthcare. Apart from healthcare, we can see it in transportation, smart city, sustainability, different kind of technology frameworks. AI is everywhere. So how can we see the artificial intelligence into its nature or in form of application? We can see that it can be subclassified into three different sectors. One is sense, second is comprehend, and third one is act. All related to this, what we can see is the AI technologies. Okay, where's the marker? Here is the marker. So you can see the AI technologies associated with it. So and the solutions. For example, in sense, what we do is we can see and we can hear. So we have computer vision and audio processing. Apart from that, in comprehend, what we have is natural language processing, knowledge representation. Whereas in act, what we have is a system which either can do a certain level of pattern recognition or can act as a expert system. So associated solution is data visualization, recommended systems, and natural language process. In comprehend, we have natural language processing, knowledge reasoning and representation. We have analytics, cognitive robotics, and similar kind of things. Okay, so how can we see AI as an example? Now we can see that it has multiple important factors. First is classifying user with a real data, such as information such as terminal type, what kind of chip it is being used. Then there's a transmission capacity, service types, buffer length, local location, movement speed, motion trajectory, etc. Apart from that, it also provides targeted service on demand. So basically, the systems learn and it can provide user specific, user centric, personalized application support. Similar to that, we have human computer interaction. In human computer interaction, what we have is converts human voice command to machine executable command. Apart from that, we have text to speech, speech to text, data mining, similar kind of feature extraction kind of applications. Apart from that, we have fraud detection and loophole prevention. In this, what happen, it is associated with security. Basically, when we are using artificial intelligence for securing networks and avoiding frauds, in such cases, if AI or deep learning is being utilized, in that case, we are going to consider this particular component. Okay, so R, what is basically, it's a very commonly known fact, but I think it is important to just have a look into it. So what is the difference between AI, ML, and deep learning? So in artificial intelligence, it is basically, a technique which enables computer to mimic human behavior. Whereas what is machine learning is basically a subset of AI. So basically, why we are going to use it? We are going to use it for statistical method to enable machines to improve experience. Whereas in deep learning is again a subset, but it is a subset of machine learning. Basically, we use multiple layer neural network to do computation and to do the recognitions. So this is basically the classification. Apart from that, what we have is a machine learning process. So in this, what we will see is that the step one is basically data gathering. Once we have a data, what we do is data cleaning, and after data cleaning, what we do is selecting right algorithm, and then we'll do building model and finalization. So basically, the it's a phase from which we have a data transformation into prediction. So all these five steps can be summarized into these three important facts, which is raw data and training, then modeling, and then finally visualization. Now in the next slide, I'll show you deep learning process. So in deep learning process is bit different from machine learning process. We can see all these five steps, whereas here the step is, so first important thing is to understand what exactly what the problem to understand the problem, because the level of complexity for the problem associated with machine learning and deep learning are very different. So understanding the problem is very important. Apart from that, we have to identify the data, what kind of data set can be utilized in such cases, and whether the data which is already available is appropriate or we need to create more data, depend on the situation. Apart from that, we have to select deep learning algorithms. Anyone can help me to understand what are the few examples of deep learning algorithms? Deep learning algorithms, anyone knows? Can you name one or two deep learning algorithms? Yes.
Yeah, Dr. Abhishek, they are typing in, the participants are typing in the answers.
Okay, okay,
They're
okay, no
writing about
problem.
CNNs and RNNs, LSTMs.
Okay, okay. So these are the deep learning algorithms. We will see. You're right. And then what happened once the model is being deployed? The what model do is we will do training the model. Once model is being trained, then we'll do the testing. So test is another component, and after test we'll see whether we'll give the data and we will see whether we are getting the information right or no. So both of them are compared in this figure. What do you see in this figure? What do you think both of them are same or both of them are different? Any idea? So you see the inputs and output is common, but where you see here is the two different steps where feature extraction and classification, which has been merged in the deep learning model. Apart from that, we can see the deep learning here. We are looking at into the training and inference model, where what we can see is there are different classes, or the data is being labeled, goes through the deep neural network. Whereas when we move forward, and then what happens, it's called forward propagation, and based on what we do, we'll calculate the losses here, and then accordingly we will manage the weight and the backward propagation. So once we have this forward backward propagation, we'll get the model weights, and that model weights are being deployed to the network. And in this case, what happened, then we have a the image which will give you the when then you give an input, and accordingly you will get an output. So what is important in this slide is basically you see that the transition. So in this diagram we will see there is a graph between data size, data set size, and accuracy. So it is not completely true that if you have more data, you will get the better output. The thing is that data should be, generated in such a way. A collection of data is very important task. But similar to that, the transition model is again very important. So you see where you have a large neural network, you have a higher accuracy, whereas in traditional neural network, you have a lower accuracy. Okay, so in this slide, what we are going to cover is convolutional neural networks. In this network, X1, X2, X3, and X4 are input layers. Whereas you can see in the blue dots are basically uh, which kind of layers? What we call to these layers? Input layer, output layer, and hidden layers. So in this, there are layers of neuron connected to the learned weights. Three layers classes: convolutional layer, pooling layer, fully connected layer. There are different kind of layers, which we will see in the diagram. Here is one class. So this diagram is now being represented here as a LNMIIT 5. So in LNMIIT 5, you have an image, and then there are different layer: convolutional layer 1, average pool, then your convolutional 2, max pool. FC is fully connected, and at last you have a softmax label. So in this diagram, what we can see is that it's a basic model. LNMIIT is a basic architecture proposed by Yan Lee Chung in 1990. It consists of input layer with dimension of 32 cross 32 cross 1. It has hidden layers in which you have two convolution layers, con1 and con2, and two average pooling layers, average pool, and two fully connected layer, FC3 and FC4. It use activation function as 10H, output layer as a softmax. In the next, you have a LXNet. In LXNet, what happen is we have the image size. This is the input layer, yellow box is the input layer. Then we have convolutional layer. Apart from that, we have max pooling. Then you have another convolutional layer, and finally, it's a how many layer? 1, 2, 3, 4, and 4. 8 layer architecture with 2 FCs and 1 softmax function. So this is the architecture designed by Alex and Jeffrey Hennington and Ilyana. This architecture consists of input layer with dimension 227 cross 227 cross 3. The network is 8 layer deep and can classify images into 1000 object category such as keyboard, mouse, pencils, and many animals. Okay, so the initially the model was trained with the ImageNet large scale visual recognition challenge, and it implemented dropout layers in order to reduce the problem of overfitting to the training data. In this model, we are using ReLU as an activation function, and at output layer, we are using softmax function. Now, another one is VGG. It's a very neat architecture. It's a visual geometry group, the full form of VGG. And the VGG network architecture was introduced by Simone and Zisman in 2015. It consists of 16 convolutional layer and is very appealing because it is very uniform in architecture. So VGG has a different kind of versions now, VGG 16, then VGG 19, and so far and so forth. Apart from VGG, then there is another network which is called recurrent neural network. It has a ability to do selective pass. Basically, it is good for sequential data and has a internal memory to process the inputs. So these are few different kind of deep learning models. I think most of you have some idea about it. Nowadays, we are using graph neural network. Apart from graph neural network, we are using transformers and all. But my intention is to focus on low power devices. So how these kind of devices, how to run these models into these devices, this is a very important component. So in this, first of all, we need to see what are the devices which can be used to run the deep learning models. Okay, so we can see this OpenMV cam. So this is a very small device which is having a microcontroller board, and it allow implementation of applications using computer vision. You can see there's a camera module here. So your whatever the algorithms you are going to put it here,
Yeah.
it can work on
Dr.
real
Abhishek,
time.
Dr. Abhishek,
Yes,
your video is not available. So are you
one second.
showing some components? So then maybe you
I
can.
can you see my slides?
No, neither your slide nor you. So
One
maybe you
No,
can
second.
madam,
stop
it is,
presenting.
it is, no, it is visible,
Once,
madam.
yeah, slides
Ma'am,
are
the slides
visible.
are visible.
Oh, it's
Slides are visible.
okay,
Okay,
okay, okay, fine,
Yes,
fine.
sir. Yes, sir.
So
It is
maybe there's
visible,
some
sir.
problem on my.
okay, it's no
All
Okay.
right, all
problem.
right.
Yes,
Some
yes.
Okay,
problem on
I
my
Yes,
think
side
it is
then.
visible.
yeah. So
Okay.
if you can't see the slides or can't hear me, just let me know. Okay, so
No,
now
sir.
this
Yeah, it's
is
It
visible.
is visible completely.
easy.
Yes,
Okay.
yes, yes.
So what is happening here is we have the OpenMB is a module which is a very half of the size of the credit card, the size of this module. It's a very low power device. It can use Python, MicroPython, C and C++. So in language wise, there is no issue. So what happened is this with this is that we need to power this up with a small battery. It can be powered up and it can be used to identify, to do the pattern recognition and to do computer vision related application. But the question is how one can do it. So there's a steps which are involved. We will see those steps in when we are going to discuss binarized neural network and quantized neural network. But this is a device which can be used similar to this. Can you name few other device where you would like to see your deep learning modules running? Can you name some hardware where you want to see uh, you know it would be better if I can run my computer vision algorithm or something, for example, time series data analysis related applications on Arduino, for example, Raspberry Pi, for example. Okay, so you can run on any hardware. So the good so another question is, what do you think, this board is a FPGA board or a microcontroller board? Answer please. Is it a FPGA or it's a microprocessor or microcontroller? It is written here, it you see microcontroller. We'll see what is the difference between microcontroller and microprocessor. It's very simple. If you have only CPU on a chip, then it is a microprocessor, whereas when you have a computer on one single chip, then it's a microcontroller. So in this, if I have to run my model into this chip, I have to follow these steps. Okay, so what I am doing here is I'm using SimSys NN. Why I'm using SimSys NN? Because I'm the processor here, this controller is of ARM, and ARM has its own firmware which I can use to deploy any deep learning algorithm on on any ARM rated hardware. Okay, so what is the full form of SimSys? Common Microcontroller Software Interface Standard Neural Network, SimSys. Okay, NN is for neural network. So you see the steps are mostly same. So whatever steps we have seen here, also you can see, there's an input layer, then there is a convolution layer, then there is a kernel, then there's a pooling, then again there's a convolution, and it goes on and on. Similar to this, what you see is I'm again drawing here in this. So in this, what happen is you have a model. So model is what you decide. Either you can go with VGG or you can go with LXNet, LeNet, ResNet, whatsoever. Train the model. Then what we do is we do the model training. We will receive the trained model. Then what we need to do is we need to quantize do the quantization. What do you mean by quantization? We need to set weights and activation function in bits. Okay, 1 bit, 2 bit, 4 bit, depends on that. Okay, so you can go from 1 bit to 16 bit, or if the word size is 32, you can go with the 32 bit as well. So once you're done with the quantization, you have a quantized model. So here you have a trained model, here you have a quantized model. That model need to be converted into binary conversion. So basically microprocessor only understands zeros and ones, so you need a binary conversion. So trained model which is being quantized, and then there's a binary model available. So once we have binary model available, we deploy it on OpenMV. So now this model is ready to deploy here on this device. Don't worry, it looks little bit complex, but I will show you step by step how this can be done. So this can be done on using various platforms. We'll see. So right now the important thing is that we understand the steps involved. So model is there, we train the model, we got the trained model, do the quantization. Now then we do binary conversion. Once the binary conversion is done, then the file is ready to dump on the target hardware. Once the target it goes to target hardware, with the camera we'll give the image. With this you give the image and it will do the classification for you. So this is how it is going to work with the SimSys NN. But this is not the only method. There are other methods as well which we are going to cover. Okay, so with this, let us discuss a little bit about SimSys NN. What is SimSys NN? SimSys NN is a library which is basically used to implement neural network on any ARM controller, basically Cortex M series M0 to M4. Any controller you can run it. Okay. Apart from that, any machine learning framework can be used to train and analyze your network. After that trained model is being converted into SimSys and an implementation. But before dumping it to the hardware, you have to convert it into which form? Binary model through quantize. So trained model, quantized model, and binary model. Once you have binary model, go ahead, you can dump it. Apart from that, it supports only small number of layers, because you see the size of device is very small. Okay, so it is very hard. So basically what I mean to say is that the computation power of this device is not too much. So there's a restriction of computation power. So in such case, you don't need, it's a better idea if you don't run a very heavy model. Okay, VGG should not, LXNet ResNet is good, but VGG, if you go beyond VGG, it will create a problem. So basically, it is good for, when you have your own small model or ANN model which you would like to deploy, no problem with that. It enables device support consistently and simple software interface to process processor and its peripherals. Same thing, slow but good. It simplifies software uses, reduce the learning curve for microcontroller developers, and reduce the time to market for the new devices. So since this NN is being used, now we will see another device which is very different from this device. So this is basically a microcontroller, whereas now the device which we are going to look into is different. This is FPGA. So if you have to work, if you are working with Raspberry Pi, Arduino, Mega, or Arduino with M4. In such cases, you can follow Simpsons NN much better approach. Whereas if there is a usability of when there's a need that you need to design your own chip level design, in such cases we have to use FPGA for deep learning. So in this, you can see figure 8 and figure 9, both of them are different kind of FPGA boards. What FPGA mean is, anybody knows what is FPGA? What is inside FPGA? Any suggestion? Any comments? It is similar to a breadboard, but rather than putting jumpers and wires, we use a program Verilog or VHDL to connect the things, okay, inside that breadboard. So so what happened here is you have a too many of logical elements, programming elements, which you program through Verilog or VLSI, using any VLSI VHDL Verilog language. So using that you can design your own chip. So you can see here's a heat sink and fan is there, but in this board only heat sink is there, other components are not there. So mostly here where you have fan and here where is the heat sink, you are deploying the main FPGA board is here. It is located here. So what is here, why we use it? Because it reduces the latency. How it is going to reduce the latency? First, you have an application. In a general case, what happen is, when your whole the design goes to the memory, from memory it comes to the chip, and so there's a latency. What I am going to do is I am going to change the chip. This chip is going to be artificial intelligence enabled, so in such cases latency will be less. So it is a low power device. Obviously, you are designing your own program specific processor or controller, so power is already regulated. It is a high throughput, frame per second is very high, flexibility to adopt new and evolving custom networks. Apart from that, it supports large image file as well. You have a security encryption and all other things are there. So this is an overview of an FPGA. What do you find inside this chip is something like this. So what we have is that you can see the full form is Field Programmable Gate Array. It has millions of logical elements, thousands of embedded memory blocks, thousands of DSP blocks. So DSP is digital signal processing blocks, and basically what it says is that, so there are these strips. Okay, these strips, if you go you look into it, you will see the logical elements. So what happen is that here inside the same chip you have memory components, you have DSP components, you have your transceiver, lot of component which can be utilized to design a intelligent hardware. How? So we will see this with the help of this case study. So we here what we do is we do the data collection. Then what we'll try to do is we will use two-hand gesture recognition using binary neural networks. Then we will see in another work that there's a static hand gesture recognition. Then we'll see dynamic hand gesture recognition. We will see sign gesture detection and classification, and finally we will see whether if the signs can be converted into sentences or no. Okay, so first step is dataset collection. So Indian Sign Language, usually, when we start with a very simple words. For example, ASEANAR, ASEAN, Assembly, SEIC. So Hindi alphabet. Apart from that, we can go with A, B, C, D. So this is how you can categorize. So first is always first data set is always simple. So 1 to 10, A to Z, us, ASEANAR, Ka, Kha, Ga, all those kind of things. So the another question was that if now we know what we need to have, then there's a problem whether we should go with a one hand or we should go with a two hand. So usually when people in community, speech impaired community, when they communicate with two hands. Okay, so in most cases we are using two hands, but some gestures are of one hand. So considering two hands will be very helpful. Why? Because if there is one hand, again it is going to be recognized, and when for some certain gesture if there are two hands, it is again going to be recognized. So dynamic ISL, Indian Sign Language two hand gesture, we have 12 classes to represent 12 months. We have different kind of videos collected by normal web cameras, and then we have different kind of signers. So we want to identify whether the complexion of skin, background, face, all these things, whether how to eliminate them. So for that we are going to use that with W two hand Indian Sign Language. This is again our data set. We have 14 categories representing the words, which is the B this diagram, and videos are gathered for each class with 4 to 15 different signers, 4 to 5 different signers. Sorry. So similar to that, we have two hand sign language representation of A to Z and other alphabets. Apart from that, we have 10 static gesture representing numbers from 0 to 9. So we have total 1700 gestures per category. Then we have 50 categories of gesture representing vowels and consonant in Hindi. So last one is Hindi. You can see E is written here. Okay, so now two hand gesture recognition using binarized neural network. So basically what happened in this neural network is basically reduced computation cost. So deep learning CNN are powerful and widely used in sign language recognition. It's very known fact. The deployment of these networks on resource limited devices major roadblock due to huge memory and power requirement. Now what binarized neural network does is that it reduces computation complexity during model training and are feasible to be run on targeted embedded platform. So this method was first proposed by a scientist who designed binary net architecture where both weights and activation are binarized. Either you can have -1 or you can have +1. That's it, nothing else. So your bitwise multiplication are performed using 1 bit XNOR between binary weights and activation to speed up execution time throughout the model training. So you can see here what do we have is -3 goes to 0.5. Now it has been reduced to 1. Okay, here you have 0.25, and you can see similar to minus, so it is less. Again you minus 0.1 reduced to 1. So again you can see 0.9 reduced to 1. So you have only two values, either +1 or -1. Okay, so this is the model which we have been proposed. So in this model, what we have is basically you can see the 4 different blocks, whereas the first block is basically the real, either you can collect the data or you can do the real-time recognition, both can be done. So you have to collect the data through webcam, classify it, then what your data pre-processing block. So you have to do original image, then image cleaning, skin segmentation, thresholding, all those components need to be implemented. Apart from that, what we have is a binarized neural network architecture. So this architecture, like that's the reason why we were discussing ResNet LeanNet before. So again you can see it's a layered architecture. So in this, what we do is finally you have a final class probability or a software classifier. Once the model goes through this, we will get the appropriate results. Okay, so in this you can see result analysis. BNN learns better throughput throughout the training as compared to CNN, and in the end the accuracy of both model is nearly about 99%. So you can see the recognition on the real time. Then we have a static hand gesture recognition on FPGA. So in this model, what we have, so there's a no movement of the hand. The gesture is the constant. So hand gesture is constant. So in this, we are using RGB raw image that are passed through pre-processing block to the segment. The hand region using skin color filtering. The skin color images are used as an input to QCNN architecture for gesture classification. The entire QCNN, Q stand for quantized. Architecture is stored in on-chip memory of FPGA and tailored for the sign language application scenario. Here you can see the block one, your data preparation. Again, the same step which we took in BNN. And in second step, what we are doing is data pre-processing. So basically in this, we are converting RGB to HSV. Again, doing pre-processing steps. After pre-processing, model goes to training set, validation set, and test set. Goes to convolutional layers. So after this, what happen is the model goes to FPGA based QNN accelerator, and from accelerator goes to test set and train set, and all the model is been basically deployed, and now the classification will happen. So the camera is connected to this FPGA board, and the model is been already deployed. Now the motion recognition will be done on the real time. So this is a hardware setup and results where you can see that on three different, so last one is FPGA, whereas one is GPU and one is CPU. The model has been compared. So with the same, where we are getting the better performance, any idea where latency wise, where we are going to have less latency? Any idea? You looking into the table, where do you see latency is very less? On FPGA. Okay, so the model setup is pretty much easier. Here you can see the gestures, whereas in the pink one is a pink board. The name of the board is Pink Z. Webcam, normal web camera of Logitech, if I'm right, and then all the so it is being connected to the system, whereas you can see the camera webcam is connected to the FPGA board, and we are getting power from the PC in this particular case. Okay, so dynamic hand gesture recognition on low power devices. So in this model, okay, so what we are going to use is Google Media Pipe. Google Media Pipe is another important Google Media Pipe. Anyone has heard before about Google Media Pipe? Google Media Pipe,
Yes, sir.
yeah. So the question is that if I have to choose, if I have to work for sign language recognition, what should I choose? If I'm going to work with Google Media Pipe, should I go with a FPGA or should I go with other board or like microcontroller or microprocessor? How do you select your hardware? This is very important question. How you are going to select an hardware? So in certain cases, when there's a limitation of there is no limitation of memory, or you know that you are going to use more computational power and you need large memory, usually we don't use FPGAs, we use the microprocessors or microcontroller with a certain memory, sometimes laptop as well. Okay, when there's a restriction associated with constant associated with the memory size, computation power, and similar things, in such cases we have to decide whether you would like to go for FPGA or no. So another important thing with FPGA is that it is very hardware specific device. What I mean to say is that if you know Python, you can easily work with Raspberry Pi, Arduino, or different other kind of board. Whereas to design a IP core on FPGA board, you need to be have good knowledge of Verilog and VHDL. So usually you can see in this diagram which board we are going to use. Any idea which board we are using? Here is the board. Raspberry Pi is what we are going to use here. So we are connecting Raspberry Pi to the camera, and here from here we are beginning. Here again the dataset preparation and augmentation, pose feature extraction, propose architecture, deployment on edge devices, and what is happening is that there are two. So media pipe is another model through which what we do is we create a skeleton on hand or on face on wherever. So it's create a skeleton. So it's a product of Google. So pose data, once we have a pose data, we drop unwanted data, then we consolidate all the chips and pickle storage and data loader for the training. Okay, so what is basically happening here is can be seen through a video. One second, I can show you this. Okay, okay. My screen is visible or no? Can you see it?
Yes, sir. Yes.
Okay.
Yes, sir. Yes.
Okay. Anybody can help me to. So you see what is happening here? There's a subject standing here, and with this you can see the subject. So there is a skeleton API or media. So skeleton API is working. So all those, there are few, the dots are feature points, and what happen is that there's a displacement. Based on this displacement, you put your hand. So a name of asana is coming. See, apart from that, what it is showing is the correction, whether you are doing it good or no. If there's a wrong, put your hand straight. Something like this is coming. So this is basically done on a simple single board computer. You're getting frame per second, everything. All the data, related data has been there. So right now it is coming as a text, but can be converted into audio. Okay. So this is how media pipe basically works. Okay, again come back to our slides. So here we have a video augmentation techniques where applied. So these techniques are applied to the data sets to improve detection accuracy. So again, you have a RGB videos utilized as an input for skeleton feature extraction, and model has been utilized. Apart, so what this diagram is saying is that you use whatever model you would like to use. Finally, what you need to do is you need to do quantization. Quantization is very important step. Okay, whatever the train model is, again do the quantization. Once it is been quantized, you need to load the model to the target hardware. Once it model is been dumped to the target hardware, then only you can see whether the model is performing right or no. Sometimes what happen, model works very nice on the host system, but it doesn't work appropriate on the target system, whereas the model is supposed to work good on the target system to achieve. So if there is certain problem, then what are the steps which we should do? Suppose my model is working very good on the host system, but it is not working good on the target system. In such case, what should I do? Any idea? Anyone? All I can do is to go back and check whether where's the problem, whether I so if I have when I do quantization, maybe I'm using 4-bit weights rather than 4-bit weights. Is it possible to use 8-bit weights, and then I'll see whether I'm going to get better accuracy or no. So it is mostly hit and trial. Sometimes logic works, but sometimes you don't know how it is going to work. So hit and trial is the final approach. So you do a lot of model tuning, and then only you can realize whether the model should work fine or no. Okay, so this is another experimental setup. Now you see what you are going to get is when you are using Raspberry Pi with a GPU, you are getting inference time is too much. Okay, 500 millisecond, 500 millisecond, whereas in CPU it is 166 millisecond. Why so? Why? Anyone can give me a reason? Any reason? Due to computation power. Okay, so here you see we have March, May, June, October, all those months. It has been done through dynamic hand gesture recognitions. So in this work, what we have sign gesture detection and classification on FPGA. So this is again, so in the previous model, we were on Raspberry Pi. Now in this model, what we are going to do, we are going to work on FPGA. So we are using tiny YOLO. So there's a YOLO, you only look once. So YOLO has a model called tiny YOLO, which is lightweight model, a 9 convolutional layers with 5 max pooling layer for feature extraction and final layer used for detection. So you can see this is a model is here you can see con 2D max pool, con 2D max pool, and finally you have a point-wise convolutional 2D. Then this model is how it is going to look like. So you can see on FPGA we have a one is processing system, and then we have a programmable logic. Programmable logic is where your Verilog code would come, and this is a ARM processor which is already been embedded to the FPGA chip. So the framework, if it is going to be Linux, Xilinx, in case of Xilinx, we are going to use VTIS AI. So through this platform, we quantize the trained model, we compile the quantized model, and then we deploy the model on FPGA. Okay, so these steps are 3 steps, but took a lot of time. I'll demonstrate how this can be done. Okay, so gesture detection and classification result, we have on FPGA we have a model. In that model size is 4.6 MB, and before quantize the model was 17.9 MB. So you see after quantization there's a drastic size difference, which is very beneficial, whereas what you see is that 64 you before quantization your accuracy was 64.2, whereas after quantization the accuracy goes to 61.2. So this is a Kriya board, very nice board from Xilinx. On the same board, we have been deployed the same model. So there's a question whether you should like to compromise with this level of accuracy or no. I think there's a difference, but it is not that much accuracy wise. Model accuracy should be much higher compared to 60 something in 60s. Okay, say sign language recognition and translation. It now in this work, what we are going to do is that we are going to use automatic sign language to regional language translator system. So in this we are using so you see there are gestures, not just one gesture, but you will see I Indian woman. So I am an Indian woman should be the sentence, but here you make a gesture of I Indian and woman. So based on that, you do the feature extraction again the same model process. So train the model. Once model is being trained, NLP model need to be implemented. Now we have a computer CNN. Then you need to implement NLP. So with this TCN model, what happened is I, Indian woman, is being recognized. With NLP, all these fillers came into the picture. I am an Indian woman. So it works good, not for all and every sentences, but for some sentences it works very nicely. So temporal convolutional network is another model. It focuses on extracting temporal feature from the data. Two layer of TCN, one dense layer and a softmax layer. So this is the real-time results. Hello, 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 how? Hello, how you? So once hello, how you have been recognized, it starts forming a sentence. Hello, how are you? In the same window, you can see it is trying to form a sentence. So you happy beautiful house. So that doesn't make any sense, but still it start, are you happy with the beautiful house? You are happy and beautiful. So they are two different. So again, not making sense. We are still working on this particular problem. We are trying to make, best out of the gestures, but still it is very challenging, but some form of sentence formation has been done. Okay, so there I have some video demo as well for you. Maybe these demos will be, let me show you some good things. Okay, I want to show you, what do you want to see? Sign gestures or this one? Now tell me what is happening in this video. What is happening in this video? Anyone? What is happening here? Anyone?
Surya Namaskar. One student is performing.
There's Shanka Prakshalam. Both of them are doing the same yoga, but their postures are different. So we are, the good thing is that in the single window, in the single frame, two different posture have been recognized. So you see here for person one and person two. So we are recognizing the pose, and also we are working on the accuracy side as well. At the same time, not so multi-object, multi-pattern recognition with the low power devices. Okay, this is one. Another thing what I want to show you is now sign hand gestures. So okay, so the Hindi alphabets. So sometimes, she is my student, her name is Mohita, and so now you can see, different kind of gestures have been performed. Now Hindi, so it there's a very tiny difference between two gestures sometimes, so it is very hard, but so far successfully done. Kha. Okay, then what do we have? Okay, then I can show you YOLO, tiny YOLO, how tiny YOLO is working on the target hardware. So all other gestures have been recognized. So for lightweight YOLO, you need to execute tiny YOLO. Okay, apart from that, if you want to see how to run a deep learning code on FPGA, then this is the right. So you can pick it from any GitHub. So model has been trained here. So once you train the model, you will get two files. One is called weight file, another one is called bias file. So these two files are which you are going to use for quantization. So weight and bias files are very important files which you will get when you run it on the host PC. So now Vivado HL has been opening. These are the performance estimations, and all other details which came into the picture once you run this file. Hardware utilization in form of DSP, memory, and all can be managed, but we need to we are already working on a constant environment, so there's not too much of scope. In worst case scenario, what we need to do is we need to change the target hardware. So now once you do it, this is the diagram. This how you are going to get it. So now connection need to be done. So you can see drag and drop. Finally, what once the model has been ready, what you need to do is to generate the bit stream. So now, so your hardware design part is done, and now the same software development environment is now going to be popped up. So with this environment, what we do basically, we'll try to run the application component of the program. So this port number is important because your FPGA is connected to the board and it should not show COM1. It should always show something rather than COM1. That's the only way to to find this. Or you can go to device manager and then you can check it. So it's a lengthy process. I mean, it looks very simple in 4-minute video, but it took a lot of time, lot of effort. Okay, now if I have to show you whether you want to see this, how it works on hardware, basically microcontroller. So we are using a STM board. STM are pretty much industry standard. So this is one demo where we are using TensorFlow Lite. So this code is going to work on a host computer and finally need to be deployed into the target hardware. So now we are working on the host side. So we run a TensorFlow Lite which will again give you weight and bias file. Same weight and bias file need to be quantized. So the steps are mostly same. So so what happen is that the cube environment, it opens, it pops up this you know window. So it looks something like this. So here you select the board and hardware selection. Then you give the project name, choose the language.
So if this works on TensorFlow Lite, will it definitely work on this device?
Yeah.
Physical devices.
Yes. This is not the simulation. Please try to understand. There's a IDE, Cube ID of ST Microelectronics. So what happen is when you are going to work on any device, the original equipment manufacturer will give you the IDE which you are going to use. So ID basically for STM Cube is a ID for all the ST microelectronics devices. For Texas Instrument, there is a Code Composer Studio or Energia. You can use both of them. For Raspberry Pi, Visual Studio is convenient, or Eclipse, any kind of Eclipse environment is good. So this is not a simulation. This is how the pinout going to look like when your code is running. This is how your pinout is going to look like. So this will just be represented here as it is. There has nothing to do with the coding component.
And suppose, sir, we want to measure the energy consumption also. Then is it possible using this ID?
Yes. Yeah. Energy consumption. So when you are, there are two ways. First is you use a JTAG, or you go to the debug mode, and then you can use the devices, or then there's a USB device which you can connect to your target hardware, and it will show you when the application is running how much energy in watt is being consumed.
Okay, sir. Thank you.
So don't bother about what these things are coming. These are, so you need to, if you are going to use network, name it. Okay, these are the steps which are going to be there. So the model name, the hardware name. So STM32 cube is a ID which we are going to use. Now what it is going to do is it will simply take this TF Lite model. Wherever the TF, you remember in host we were running TensorFlow. So the model TF Lite model need to be there. So now once it is been browsed or located, then it will. So this is how it is going to look like, which basically means the model is being deployed. It will take some time analyzing network. So there's a so now you see everything is coming here. All this. So this is how it is what going to look like. So basically in this way you are going to use this ID only when your board is connected. So what is the intention of using this ID? Because I have already done my deep learning code on localhost, local PC, like for Google Colab. Then what's the sense of using this ID? Because I want to dump that code to the target hardware. In this case, it is STM32F this hardware. So now still it has been connected and things are going on. So there are multiple steps. Nothing is complicated in this. First, sometime it will take, it will be not easy, but slowly, slowly. So whatever you do, the changes here, it will be coming out into your code as well. So here you have library, C code, file is ready. Now you can simply dump. Now this is still it is on a host because the ID is installed in the host PC. So once you click on run, it will go to your target hardware. Yeah, you see this is the hardware. Now again here from here it ELF and then it is done. Done to the hardware. Nothing else is left. Okay, I think if there are any doubts or any question associated with today's lecture presentation, please let me know. Yeah, I think I have covered most of it.
Participants, please, the floor is open for you to ask questions.
Two questions, ma'am.
Yes.
Abhishek sir,
Yeah.
one in case when we like flash a network onto an FPGA, what kind of a gain do we see, as in terms of speed, and can we train a network on a FPGA also?
Okay, so I haven't done the gain analysis yet, so I don't know how to respond to that. But I have done power analysis. We have shown you on the slides already. And what was your second question?
Uh, no, actually, this is a continuation of the same question that uh, 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 can we train a model on an FPGA as well? I mean,
Okay.
is there any benefit of training as well, or do we first train the network and then get weights and biases and then flash them on an FPGA? So this
That
is
the only way is to, so far what I have gone through and what I have done is that the best way or the only way which we found is to run on host, create a weight bias file, and then quantize it and then finally put it into the FPGA. See, for hardware we use simply binarized model BNN, or in FPGAs we can go with quantized model, and then there is spiking neural network other model. The only way is to do the most of the part on the host and then dump it on the target.
right, right. I asked because see, most of the power consumption that we see goes during the training process, right? I mean, when we
Yeah,
talk
yeah, yeah.
about all these
Yes.
chat GPT, etc., etc.
Yeah.
That's why I was asking. Okay, so second question, sir, is related to a video that you showed in sign language.
Mm-hmm.
That as in when the person, as in the sign language speaker was doing the signs, there was the
Yeah.
sentences were being interpreted,
Yes.
right? So
Yes.
is there some kind of punctuation signs also? I mean, how do we detect that the sentence is complete?
Okay, so once we recognize these words, we give these words recognized pattern to the NLP model, and from there it will do the job. So it is not just computer vision,
Okay,
but
okay,
it
okay,
is
got
the
it,
combination of both. So you have a
got it.
yeah,
Makes sense, makes sense. So we get tokens. So basically, we have a converter for CNN to words itself, and then
yeah,
from words we figure
yeah.
out pattern. Okay,
So,
okay,
so
okay.
mostly as a hardware engineer, what I do is I rely mostly on the software engineers or software team. They will do the software development. We simply try to make sense of how once the model has been working fine. Now it's our duty to put it on the hardware, which is not
Right,
easy.
right.
It totally depends on when the target changes, everything changes. Steps remain
Correct,
same,
correct.
but
Hmm.
when the target is different, the whole thing need to be calibrated again.
Okay, okay, okay. Okay, sir. As a, I work in a software space, so I am very not aware of all those details. So,
Yeah, but this
yeah.
is the area where I think I find very less people nowadays. It's a good community, but when we started in 2019, there was not that much of support.
Okay,
So
okay.
I'm working in that domain.
Wow. Let's
If you
collaborate.
if you remember, I met you online in I think 2021. My guide is my supervisor is Dr. Praveen Kumar, VNIT Nagpur.
Wow. Yeah, 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 yeah. Oh, very nice. He's from our institute.
VNIT Nagpur.
Now he's in VNIT. Yeah, yeah, yeah. So
Yes.
Yeah,
you
Dr. Praveen
remember?
Kumar was earlier in LNMIIT. Yes, yes.
But now you see we were working, we were discussing about this sign language problem, no?
Yes, yes, yes. Now
Yeah.
I
And now
progressed in sentence level translation, but totally on vision based. It's not hardware based.
so, hardware, see, we have two teams. One works on software and another one works on the hardware. So one software will get success. The next important thing is to dump it on the hardware, because hardware gives you extra, speed, which you can't get when you are, how light you make a model. It will go from memory to processor interpretation. Lot of steps need to be taken. When you are going to make it on the chip level, there's a drastic different.
Yes, yes. I know that I can understand it, sir. It's
Yeah,
giving me
yeah,
less accuracy, but it's not intrusive, we can say.
yeah.
Actually, the devices that you attach to the body.
Yeah, yeah, yeah. Apart from that, we can see that Raspberry Pi and Raspberry Pico. So running again, both of them are, some very small devices. I don't want to say low power, but the Pico is really very very tiny. So running even, the model on Pico is very challenging. If we are not going on the FPGAs, but it's still on microcontroller, still it is very challenging. I
Yes.
haven't done it yet, but we are still working on it to make it more portable. Yeah, yeah. Thank you.
Sir, there is a query from Dr. Bhargavi. So, asking that can you extend your work of sign recognition to South Indian languages like Telugu?
Yes. Yeah, yeah, yeah. So we have a team, and now we have this data available on Mendeley. So we are going to utilize that. But the problem, see, I don't want to convert the sign gestures into English. So the language, so whatever it is, scripting should be also in the regional language. So this project is funded from Department of Science and Technology. Any kind of collaboration is very helpful. We already have in north side we have good collaboration. South we are also trying, but I don't know how to write in the regional languages. That's a serious target. If you would like to contribute, we will be very happy to work with you and your group. No problem.
Okay, so is there any queries from the participants?
In your work three, I guess you told that on GPU it is taking more time as compared to CPU. So what was the reason?
Okay, so reason was basically the computer architecture. What have we found? Because the GPU architecture style is completely different than because many core and multi core kind of challenges are there. So pipeline pre-processing pipeline was typically, because it's a hardwired already, so there was some challenges associated with it, which we can't do because sometimes compiler, because GPU has a different compiler. Whereas the in the Intel normal sorry, what to say this, Intel processors has a different compiler. So in GPU GCC with a different tag work. So I sometimes it's a compiler related issue. Sometimes it's a hardware related constraints which we can't change. But in FPGA we have very much of flexibility. We can design our own tool chain. We can design our own processor. Everything code is also been, in Verilog VHDL came into that level, so it is much more flexibility. But and every time you can't go on FPGA, that's another problem. So most it is always good to stay on microcontroller or microprocessor. It's very good, but चार कोर से भी काम नहीं चलता है. It's very challenging
Hmm.
with gestures and sentence. One single code, two code never works. Raspberry model, we are using model B now with 4 core, or if I'm right, 8 cores. Yeah.
Okay,
Hello, sir.
Namaste. Hello.
Uh, Hello, sir. I have a question that when we are trying with very complex models, like very large number of convolutional layers and all,
Hmm.
then we have challenge to implement that on microcontrollers, right?
Yes.
So, what is the solution for that?
So you run the whole model into Google Colab or in your host PC, no problem. Do the training testing part till there. Once it is been trained and tested, what you need to do, you need to quantize. You need to use weight and bias file, and you need to run it either on TensorFlow Lite framework or any some other framework. Those will give you two different file that was already been demonstrated, and that you need to flash.
Okay, sir.
Yes. So 90% of the task is done still on host device. Once it is being processed, done everything, then we flash it on the hardware. You can't simply take one, let's say 100 GB of data and then do pre-processing on that particular thing. It's not possible.
Okay, sir. Thank you.
No problem. Okay, initially presentation was bit slow. Now I got the pace, huh? Slowly, slowly.
Yes, sir, definitely. Any queries from the participants? Uh, I don't think that any other queries are there.
Mm-hmm.
So yes, sir. So let us then. No, I don't see any queries in the chat box also.
Okay, okay.
Yes, the recordings will be shared with you later on. Okay. Feedback form. So feedback form will be as Priti madam said. So it will be collected at the end of the FDP or maybe like on the last date of FDP. Okay.
Okay, so Dr. Nikunj, can we like wind up the
Yes.
sessions for today?
Yes.
Sure,
Obviously.
sure.
So
Thank you.
basically
Maybe,
this
yes.
maybe like okay.
Thank you, Dr. Abhishek, for joining. It was a nice, informative session. And
Yeah.
And
Thank you.
really, it
thank
is
you so
helpful.
much.
So, and you talked about like importance of AI with the overview of deep learning, including the CNN also, and you talked about low power devices like OpenMB, CAM, and you demonstrated the deployment flow in FPGAs, showcasing the practical solution for resource constrained environments. So it is a very nice and engaging talk by Dr. Abhishek Sharma. Thank you, sir. Thank you for
Thank you.
this.
Thank you very much,
Thank you for this
everybody.
information talk. Thank you.
Also, we would like to inform the participants that the session tomorrow would be at 6 p.m., right, Dr. Nikunj? And
Yes.
and
From 6 to
from 6 to
uh,
9 tomorrow. And
yes.
Professor Amit Seth from University of South Carolina would be joining us, and he would be like taking a session on neurosymbolic AI. So we hope to see you tomorrow. Please join in. Thank you and good night.
Thank you all. Thank you. Good night. So, madam, can we end the call for everyone for the time being?
Yeah, I'm just waiting for, yeah, maybe we can end the call, right? Yeah, I
Okay.
think we can.
So
Yeah.
I'm ending the call from for
Yes.
everyone for the time
All
being.
right.
Okay.
Okay.
Okay. Good night all. Good night.
Good night.